Hello there, and welcome to Nightfall Science. Tonight, we drift through the mysterious signals humanity has received from space and ask whether another intelligence may have already answered. Let your eyes grow heavy. Let's begin. An answer from another civilization may not resemble a human voice. It may arrive as a narrow line within a radio spectrum. It may appear as a brief pulse of laser light. It may be hidden inside a repeating mathematical pattern, or revealed through unusual chemistry in the atmosphere of a distant planet. It might not be intended for Earth at all. A telescope could intercept communication between two planets in another system. It could detect radar used to map a distant moon. It might notice energy released by technology operating quietly around another star. Scientists call these possible signs technosignatures. A technosignature is evidence that technology has altered matter or energy in a detectable way. Radio transmissions are the most familiar example, but the search can also include optical pulses, artificial atmospheric compounds, unusual waste heat, or structures affecting a star's light. These possibilities widen the meaning of an answer. Another civilization does not need to understand humanity's message. It does not need to know that Earth exists. Its technology may simply leave a pattern that natural processes cannot easily reproduce. Yet the present scientific conclusion remains careful. As of 2026, no SETI search has received a confirmed extraterrestrial signal, and no technosignature has been verified as the work of another civilization. NASA also reports no credible evidence that extraterrestrial life has been found, or that unidentified objects observed near Earth have an alien origin. This does not mean that every unusual observation has been explained. Some signals appeared only once. Some were recorded too weakly for a confident interpretation. Others remain interesting because several natural explanations are possible, and the original data cannot distinguish between them. But unexplained does not mean artificial. A mystery identifies a gap in knowledge. It does not identify what occupies that gap. The search for an answer therefore begins by asking a quieter question. What would a real answer need to look like? Before that question can be understood, it helps to remember what humanity has already sent. The first deliberate interstellar messages were not radio transmissions. They were physical objects. Pioneer 10 and Pioneer 11 carried small golden plaques attached to their spacecraft. Each plaque included a drawing of a human man and woman, a representation of the solar system, and a map using pulsars to indicate the location of the sun. The plaques were created in case one of the spacecraft was discovered in the distant future. They did not travel toward a known inhabited world. They simply accompanied machines leaving the planetary region, carrying a quiet explanation of where they came from. The probability of anyone finding them is extremely small. Space between stars is enormous. A spacecraft is tiny. It can pass through a planetary system without coming close to a planet, moon, station, or observing instrument. Still, the plaque transformed Pioneer into more than a scientific machine. It became a message attached to a moving object. For the first time, an artifact from Earth carried information intended for a possible intelligence that had never been observed. Voyager 1 and Voyager 2 carried a much richer message. Each spacecraft holds a 12-inch, gold-plated copper phonograph record. The records contain images, natural sounds, music, spoken greetings, and information about Earth. The selected sounds include wind, thunder, animals, and human activity. Greetings were recorded in 55 languages. More than 100 images represent anatomy, landscapes, mathematics, biology, architecture, food, transportation, and everyday life. Instructions engraved upon the cover explain how the record might be played. The diagrams use properties of the hydrogen atom as a basic unit. A map shows the sun's position relative to several pulsars. Another diagram explains how the recorded signals can be transformed into images. The message assumes that any civilization capable of recovering a spacecraft from interstellar space would also understand fundamental physics. It does not assume a shared spoken language. The record is often described as a bottle placed within a cosmic ocean. It was not designed as the most efficient way to make contact. Its chance of being discovered is extremely small. Its meaning lies partly in the act of sending it. A living world created a small portrait of itself and allowed that portrait to drift beyond the planets. The most famous deliberate radio message left Earth in The transmission came from the Arecibo Observatory in Puerto Rico. It was aimed toward the globular star cluster Messier 13, a dense gathering containing hundreds of thousands of stars. The message used binary information arranged into a simple picture. It represented numbers, chemical elements important to terrestrial life, the structure of DNA, a human figure, the solar system, and the Arecibo telescope itself. Unlike the Pioneer plaques and Voyager records, the Arecibo message traveled at the speed of light. It crossed the orbit of the Moon in little more than a second. It passed beyond the planets within hours. It has continued outward ever since, yet its destination lies tens of thousands of light-years away. Even if an intelligence within Messier 13 received the message, understood it immediately, and transmitted a response without delay, the round trip would take close to 50,000 years. No answer to that transmission can have reached Earth during the present era. The Arecibo message is already far beyond the solar system, but from the scale of the Milky Way, its journey has barely begun. This delay changes the meaning of the question, have aliens already answered us? Most deliberate messages have not existed long enough for distant recipients to receive them and respond. A civilization 50 light-years away would observe Earth as it appeared 50 years earlier. If it replied immediately, the response would require another 50 years to travel back. The total waiting time would be 100 years. A civilization 500 light-years away would need 1,000 years for the same exchange. A society on the opposite side of the Milky Way would remain separated by spans longer than recorded human history. Interstellar communication is not like a telephone conversation. It resembles writing letters across time. The sender may never live to receive a response. The people who decode the reply may belong to generations that did not exist when the original message was transmitted. This means that silence after sending a signal does not immediately reveal absence. The message may still be traveling. It may have arrived at a planet with no receiver. It may have reached a civilization that chose not to answer. A response may already be moving through space, while remaining centuries away. Distance creates a universe filled with delayed information. Every star is observed in the past, and every possible answer must cross that same distance again. Humanity has also been transmitting without intending to send a message. Radio and television broadcasts, military radar, planetary radar, satellite communications, and other technologies release electromagnetic energy. Some of that energy escapes the solar system. These emissions are sometimes described as an expanding radio bubble surrounding Earth. The image is useful, but the bubble does not have one simple boundary. Different signals possess different strengths. Ordinary television and mobile communications become faint as they spread. Their energy is distributed across an ever-growing area. At great distances, they can become difficult to separate from natural background noise. Powerful radar is different. A radar system concentrates substantial energy into a narrower beam. Recent research comparing Earth's technosignatures suggests that planetary radar has been among the most detectable human technologies, potentially visible to sufficiently capable observers across thousands of light-years when the beam points in their direction. Weaker emissions, including mobile communication leakage, would be detectable only across much smaller distances, using instruments comparable to those presently imagined. Earth is therefore not equally visible from every star. A civilization may lie inside the region reached by human radio waves and still detect nothing. It must possess a suitable receiver, observe at the correct frequencies, and look while a sufficiently strong signal points toward its system. The most detectable signals may also be the least continuous. Planetary radar beams are powerful, but they are aimed toward selected objects. They do not illuminate the entire sky at once. A distant planet must lie close to the direction of the beam during transmission. As Earth rotates and orbits the Sun, that direction changes. The signal may cross another system briefly and then move away. An observer there could receive a short, unusual pulse. If its instruments were not operating at that moment, the event would pass unnoticed. The same limitation applies in reverse. An alien civilization may already produce powerful radio emissions. Its beams may cross the galaxy while rarely crossing Earth. A telescope might need to observe the correct star during one narrow interval. The transmission may last seconds. The telescope may look a day later. Both civilizations could be active, capable, and relatively nearby while remaining unaware of one another. Communication beams create thin paths rather than filling space evenly. The silence between stars may therefore reflect geometry as much as absence. Humanity's accidental emissions also carry little obvious meaning. A distant receiver may detect energy without understanding what produced it. Modern broadcasts overlap, interfere, and become distorted as they travel. A television program is not likely to arrive as a clear moving picture. Its signal weakens and mixes with noise. Without knowledge of the encoding system, even a strong transmission may appear only as structured radiation. The first recognizable sign of Earth may not be language. It may simply be evidence that one planet produces narrow, organized, or unusually powerful radio energy. A distant observer could know that technology exists without understanding anything the technology is saying. The same may be true of the signals detected from space. The first alien answer may contain no greeting. Its artificial origin alone could be the message. Radio telescopes search for several features that might distinguish technology from nature. One of the most important is narrow bandwidth. Natural astronomical objects often release energy across broad ranges of frequencies. Stars, gas clouds, pulsars, and active galaxies create complex radio emission, but their energy usually occupies wider bands. Technology can concentrate energy into an extremely narrow channel. A narrow-band signal travels efficiently and stands out against broader noise. Human communication systems use this principle, and another technological civilization might discover the same advantage. Narrowness alone is not enough. Human equipment also creates narrow-band signals. Satellites, radar stations, aircraft, observatory electronics, navigation systems, and mobile networks fill the radio environment with artificial emission. A telescope seeking alien technology is already surrounded by terrestrial technology. Researchers must determine whether a signal comes from the sky or from somewhere near Earth. They compare observations taken while the telescope points toward the target with observations taken slightly away from it. A genuine signal associated with a star should appear when the telescope observes that star. It should vanish when the telescope moves away. It should return when the telescope returns. Local interference often remains visible in several directions. This observing pattern creates a simple test. On the target, away from the target, back to the target. A candidate becomes more interesting only when it follows the star rather than the telescope. Motion provides another clue. A transmitter resting upon a planet does not remain motionless relative to Earth. Its planet rotates, it moves around its star. Earth rotates and moves around the Sun at the same time. These motions change the relative speed between sender and receiver. The observed frequency shifts slightly through the Doppler effect. A signal may drift gently upward or downward across the radio spectrum. Search algorithms examine millions of channels and test many possible drift rates. They look for narrow lines sliding in a way consistent with a transmitter located upon a moving world. But even this behavior can be imitated. A satellite moving around Earth also produces Doppler drift. Electronic interference can change frequency as equipment warms or cools. Several terrestrial signals can combine and create new patterns that appear unusual. No single technical feature confirms an extraterrestrial source. The signal must survive several filters. It must appear in the correct direction. It must behave consistently. It must avoid known human frequencies. It should ideally repeat. And it should be observed by another telescope located far from the first. Independent confirmation is essential because every observatory has its own local environment. A signal detected in Australia and again in North America would be much harder to explain as nearby interference. The first observation creates a candidate. Repetition begins creating evidence. This requirement makes brief signals difficult to interpret. An artificial transmission may occur only once. A civilization could send one short pulse toward Earth and never repeat it. The signal could be genuine while remaining scientifically unconfirmed forever. Science requires another opportunity to measure it. Without repetition, researchers cannot refine the direction, examine the polarization, compare observatories, or test whether the pattern returns according to a planetary orbit. One event can remain intriguing. It cannot easily become proof. This is why the most famous candidates occupy an unusual space between imagination and evidence. They appear sufficiently organized to attract attention. The signal becomes a small fragment without enough surrounding information to reveal its source. Nature is also capable of producing extraordinary radio patterns. When pulsars were first discovered, their regular pulses appeared so precise that an artificial origin was briefly considered. They were later understood as rapidly rotating neutron stars whose beams sweep across Earth like distant lighthouses. Fast radio bursts offered another unfamiliar phenomenon. They release intense pulses lasting only fractions of a second. Some repeat. Others have been observed only once. Evidence now connects at least some of them to highly magnetized neutron stars called magnetars. The history of radio astronomy repeatedly shows that a signal can appear engineered when its natural mechanism is unknown. This does not make the search for technology unreasonable. It makes the universe more inventive than early expectations. Every natural explanation improves the search. Once pulsars are understood, their behavior can be separated from artificial transmitters. Once satellite interference is catalogued, software can remove it. Once a new astrophysical phenomenon is recognized, future candidates can be compared against it. False alarms become part of the instrument. They teach researchers what a real answer must survive. Humanity has already recorded signals that passed several early tests. The WOW signal rose and fell in a pattern consistent with a fixed source crossing a telescope's beam. It appeared narrow and strong, then never returned. BLC-1 seemed to arrive from the direction of Proxima Centauri. It occupied a narrow frequency and drifted over time. Deeper investigation connected it to a larger family of signals consistent with human-made interference, and extensive follow-up observations found no recurrence. Artificial intelligence searches have also identified signals missed by older pipelines. When telescopes returned to their source regions, those candidates did not reappear. None became a confirmed answer. Each improved the method used to evaluate the next one. The lack of confirmation is sometimes interpreted as evidence that nothing has been received. A more accurate statement is subtler. Many signals have been received. Some are natural, many are human. A few remain unexplained because the available information is incomplete. What has not been received is a signal that survives every test required to identify extraterrestrial technology confidently. That distinction is the center of the entire question. Perhaps an answer arrived but was not recognized. Perhaps it appeared once and vanished into an archive. Perhaps a signal classified as interference contained a real transmission hidden beneath terrestrial noise. Perhaps an alien message uses a form of encoding that appears random to human software. These possibilities cannot be eliminated completely, but they cannot be treated as discoveries without positive evidence. A lost answer and an answer that never existed can look exactly the same in incomplete data. Researchers must follow what can be measured, rather than what could be imagined. Modern surveys produce enormous data sets. A radio telescope can monitor millions or billions of narrow channels. Each observation contains terrestrial interference, natural emission, instrumental noise, and occasional unusual patterns. No research team can inspect every signal by eye. Automated pipelines remove familiar interference and select candidates for closer analysis. Machine learning systems are now being trained to recognize patterns that earlier methods may have ignored. This creates the possibility that old data can become scientifically new. A signal recorded years ago may be found by an algorithm developed tomorrow. An observation gathered for one purpose can be searched again for a different kind of technosignature. Breakthrough Listen has already used artificial intelligence to identify signals of interest that were missed by traditional searches. Those particular candidates did not repeat during follow-up observations, but the method demonstrated that the same sky can reveal different patterns when examined with different tools. The first confirmed answer may therefore be discovered after it arrives. A telescope records a faint pattern. The data are stored. Years pass. A new search method notices that the pattern drifts in an unusual way. Researchers examine other observations of the same star. A similar signal appears at another time or frequency. The telescope returns. Another observatory listens. The pattern repeats. What began as unnoticed information gradually becomes evidence. This possibility makes astronomical archives part of the search. The past has not been examined only once. It can be revisited. Still, no hidden signal can be declared real before it is found and verified. The idea that an answer might be waiting in stored data remains a possibility, not a conclusion. As of now, the confirmed record remains quiet. The search has detected no extraterrestrial transmitter. It has found no verified laser beacon. It has identified no artificial structure around another star. It has received no message that independent observatories can reproduce. But the search has also examined only a small portion of the possible sky. Frequencies, signal types, and moments. Breakthrough Listen and other programs are expanding that coverage with broader surveys, all-sky monitoring, improved receivers, optical searches, and new analysis methods. The most recent official updates continue to report no confirmed technosignature, while placing stronger limits on some types of detectable civilizations. This is where the first part of the journey settles. Humanity has sent plaques, records, radio pictures, radar beams, broadcasts, and countless accidental traces of technology. Most deliberate messages have not traveled far enough for a response to return. Most accidental signals are faint and difficult to detect. A real answer may be brief, narrowly directed, strangely encoded, or hidden among natural and human noise. Science therefore asks more from a signal than mystery. It asks for direction, repetition, independent confirmation, behavior consistent with a distant moving source, and a pattern that known natural processes and terrestrial technology cannot adequately explain. No candidate has crossed every step, but several have approached the beginning of the path. The most famous of them lasted only 72 seconds. It rose gently from the radio background, became unusually strong, and then faded. It has never been heard in the same way again. Whether it was an answer, a natural event, or a brief piece of earthly interference remains uncertain. For now, it rests within the history of the search as a reminder that one signal can hold attention for decades without becoming proof. The most famous possible answer from the stars did not arrive as a voice. It arrived as 6 characters printed on paper. On August 15, 1977, the Ohio State University Radio Observatory was conducting a routine search of the sky. Its radio telescope, known as Big Ear, listened for narrow signals that might stand apart from ordinary cosmic noise. The telescope was not tracking one chosen star. It remained fixed while Earth's rotation carried the sky through its observing beam. A distant source would gradually enter the beam, rise in strength, reach a peak, and then fade as the rotation of Earth carried it away. That evening, something followed this pattern almost perfectly. The signal appeared within one narrow frequency channel. It grew steadily stronger, reached an extraordinary intensity, and then declined. The entire recorded event lasted 72 seconds. Several days later, astronomer Jerry Amon examined the observatory's printed data. Among the long columns of ordinary measurements, he found a sequence that immediately caught his attention. 6EQJ5. He circled the characters in red ink. Beside them, he wrote one word. Wow. The name remained. The 6 characters were not a message written by another civilization. They did not translate into words, numbers, or coordinates. They represented signal strength. Big Ear recorded the intensity within each frequency channel over successive 12-second intervals. Low values were shown with numbers. Stronger values were represented with letters. The sequence described a signal rising from the background, becoming remarkably strong, and then fading again. At its peak, the signal was approximately 30 times stronger than the surrounding noise. The shape of that rise and fall closely matched the response expected when a fixed celestial source moved through Big Ear's beam. The printed sequence has sometimes been treated as though it were an encoded alien phrase. Its true meaning is simpler. It is a tiny graph compressed into 6 symbols. The first character, 6, marks the beginning of the rise. The letter E shows that the intensity has increased. Q and U record the signal climbing toward its peak. J shows it beginning to decline. The final 5 records the fading edge. Read from left to right. The symbols trace a gentle hill. That hill is one reason the event remains so compelling. A brief burst caused by nearby electronic equipment might begin or end suddenly. The wow signal behaved as though the telescope's beam was moving across a compact source located at a fixed point in the sky. Earth rotated. The source remained still. The signal slowly entered and left the telescope's field of view. This does not establish that the source was artificial. It does suggest that the event was not a simple burst generated inside the observatory. Something appeared to be shining in radio waves from a particular direction. Then it stopped. Big Ear possessed 2 receiving beams arranged so that the same location in the sky normally passed through one beam and then the other a few minutes later. A continuous celestial source should therefore have appeared twice. The wow signal appeared in only one beam. When the second beam crossed the same region, nothing comparable was recorded. This means the source either switched off during the interval or changed dramatically before the second observation. That behavior is difficult to interpret. A natural source might flare briefly. A transmitter might send one pulse and stop. Interference could appear under unusual conditions and then disappear. The single detection does not distinguish among them. It simply shows that whatever produced the signal did not remain steadily visible. The frequency made the observation even more interesting. The WOW signal appeared close to 1420 MHz, the natural radio frequency associated with neutral hydrogen. Hydrogen is the simplest and most abundant element in the universe. Clouds of it fill regions between stars. A hydrogen atom can undergo a subtle internal transition and release radio energy at a wavelength of about 21 centimeters. Radio astronomers use this emission to map hydrogen throughout the Milky Way. Long before the WOW signal appeared, some SETI researchers had suggested that the hydrogen frequency might serve as a natural meeting place for interstellar communication. A civilization developing radio astronomy would probably discover the hydrogen line. It would recognize the frequency as universal rather than dependent upon one planet's language, history, or units of measurement. A transmitter placed near this cosmic landmark might be easier for another civilization to notice. The WOW signal therefore appeared near a frequency already considered symbolically and scientifically important to SETI. It was narrow, strong, and shaped like a celestial source crossing the telescope's beam. These features made it unusual. They did not make it extraterrestrial. Natural hydrogen emission is usually spread across a wider range of frequencies than the signal Big Ear recorded. The WOW event occupied a channel narrower than 10 kHz. At the time, extremely narrow cosmic radio emission was difficult to explain through known astronomy. Technology, however, routinely produces narrow signals. A radio transmitter concentrates power within a limited frequency range. It does this because a narrow channel uses energy efficiently and makes the signal easier to distinguish from noise. The observation therefore contained a combination SETI researchers were trained to notice: a compact source, a narrow frequency, a strong intensity, a location near the hydrogen line, and a rise and fall consistent with the telescope's beam. It seemed almost designed to become famous, yet the most important feature of a genuine discovery was missing. The signal never returned. The Big Ear telescope continued observing the region. Other astronomers later examined the same part of the sky with different instruments. No observation reproduced the event. Radio astronomer Robert Gray organized several follow-up searches. The Very Large Array in New Mexico examined the area. A radio telescope in Tasmania searched for periodic or intermittent emission. These studies placed limits on repeating signals within the region, but they did not hear the WOW event again. More recent coordinated observations by the Green Bank Telescope and the Allen Telescope Array also failed to recover it. The silence after the signal created its mystery. A repeating transmission could be studied carefully. Astronomers could refine its position. They could measure its exact frequency, bandwidth, polarization, and drift. Different telescopes could confirm that it came from the same celestial direction. A one-time signal leaves only its original record. The event cannot be paused. It cannot be observed from another angle. It cannot be measured with modern equipment. The paper printout contains 6 intensity values within one frequency channel. That was enough to reveal something unusual. It was not enough to reveal the source. No audio recording exists. Big Ear did not save the signal as sound. The familiar beeps used in documentaries and videos are recreations rather than recordings of the original event. The true WOW signal was silent to human ears. It existed as radio energy converted into numbers and letters. A machine noticed the energy. A person noticed the pattern. Everything humanity knows about that moment rests upon a small section of printed paper. The signal came from the general direction of the constellation Sagittarius. This direction looks toward a rich region of the Milky Way, where many stars and clouds lie along the same line of sight. Big Ear's design did not provide one perfectly precise point of origin. Because the signal appeared in only one of its 2 beams, 2 nearby regions remained possible. Thousands of stars may occupy or lie behind those areas. Choosing one particular star as the source is therefore difficult. A sun-like star identified within the possible region has sometimes been suggested as a target for further observation. Breakthrough Listen conducted searches around that candidate using modern radio telescopes. No signal resembling the original event was detected. The lack of repetition does not prove that the 1977 signal came from nowhere. It means the source may have been temporary. If a civilization sent a narrow beam, Earth may have crossed it only once. The beam could have been aimed toward another planet. It might have swept through space as a transmitter rotated. Big Ear could have intercepted a brief fragment of communication never intended for humanity. The source might also have transmitted periodically. Its period could be longer than the intervals examined by later searchers. A beacon might operate once every year, century, or 1,000 years. The next pulse could have passed while no telescope was pointed toward the correct region. A civilization might also have ended the transmission entirely. The 1977 event could have been the final pulse from a machine that no longer operates. These possibilities preserve the alien interpretation. They do not strengthen its evidence. Any rare or non-repeating signal can be protected by imagining that the transmitter switched off at exactly the right time. Science needs a prediction that can be tested. A repeating signal provides one. A permanently vanished transmitter does not. Natural explanations face the same difficulty. The event could have been a brief astronomical flare, but no known source was clearly identified at the time. It could have resulted from terrestrial radio interference, but the signal's smooth rise and fall resembled a fixed source crossing Big Ear's beam. It could have reflected from an object in space, but the necessary geometry and lack of repetition create additional questions. Comets have also been proposed. A comet releases hydrogen as sunlight breaks apart water molecules within its surrounding cloud. Because the WOW signal appeared near the hydrogen line, researchers suggested that a comet passing near the observed region might have produced it. Later radio observations confirmed that cometary hydrogen can be detected near this frequency. However, the proposed explanation has not gained broad acceptance as a complete solution. Ordinary cometary hydrogen emission is generally broader and more extended than the exceptionally narrow, strong event recorded by Big Ear. A natural origin may still be correct. The exact mechanism remains uncertain. More recently, researchers have proposed a different astronomical explanation involving small clouds of cold neutral hydrogen. Archived observations from the Arecibo Observatory revealed narrow features near the hydrogen frequency from several directions. These features were much weaker than the WOW signal, but showed that small hydrogen clouds can produce emission with some similar characteristics. The researchers suggested that a powerful transient event, perhaps a magnetar flare or a soft gamma repeater, could briefly stimulate a hydrogen cloud to emit a much brighter and narrower burst. The process would resemble an astronomical maser. A maser is related to a laser, but it operates at microwave or radio wavelengths. Energy excites atoms or molecules, allowing them to amplify radiation coherently. Under rare conditions, a sudden energetic event might cause a cloud of hydrogen to brighten dramatically at its natural frequency. Such a flare could be narrow, powerful, brief, and unlikely to repeat. These are all features associated with the WOW signal. The hypothesis is scientifically appealing because it attempts to explain the event using known physical ingredients. Hydrogen clouds exist. Magnetars and other transient sources release enormous bursts of energy. Stimulated emission occurs in space. The combination may be rare enough that no similar event has been recognized easily, but the proposed explanation is not yet a confirmed solution. No astronomer observed a magnetar flare and a hydrogen burst at the WOW location in 1977. The mechanism is inferred from later data and physical modeling. It provides a possible natural pathway, not direct evidence of what happened that night. A 2025 reanalysis used archival Ohio SETI records to revise several estimated properties of the event. The study narrowed and slightly shifted the possible sky location, estimated a stronger peak intensity than earlier reconstructions, and argued that the signal's frequency and behavior may favor a galactic astrophysical source over ordinary local interference. The same analysis supported the possibility that small cold hydrogen clouds can create narrow signals related to the event. This changes the mystery without ending it. The signal may become less likely to have resulted from a simple nearby transmitter. It may become more compatible with an unknown or rare natural event inside the Milky Way. But a galactic source is not automatically biological. Stars and interstellar clouds belong to the galaxy too. A natural explanation can come from the direction of Sagittarius, follow the telescope's beam, and disappear before a second observation. The universe contains brief events that early instruments were never designed to recognize fully. A rare natural source may be observed only once because the phenomenon itself is rare. This is the repeating lesson of astronomy. Pulsars initially appeared so regular that intelligence was considered briefly. Fast radio bursts seemed unlike known sources until evidence connected at least some of them to magnetars. Gamma-ray bursts remained mysterious until better instruments located them in distant galaxies and linked different types to stellar explosions and mergers. The first observation of a new natural phenomenon often appears alone. Its category does not exist yet. Without related examples, scientists cannot see the family resemblance. The WOW signal may belong to a natural family that modern astronomy has only begun to recognize. Or it may remain unique because the event that produced it was artificial. The available evidence does not choose between these possibilities decisively. The signal's location near the hydrogen line deserves special care. An artificial transmitter might choose that frequency deliberately. A natural hydrogen cloud would produce energy there automatically. The same feature supports both interpretations for completely different reasons. For technology, the frequency is a universal landmark. For nature, it is the characteristic voice of the most abundant element in the cosmos. This makes the event beautifully ambiguous. The signal appears exactly where one might expect a civilization to announce itself. It also appears exactly where hydrogen is naturally able to glow. The answer depends upon the details that the original observation could not preserve. Was the signal perfectly monochromatic? Did its frequency drift? Was it polarized? Did it contain rapid modulation or information inside the broader pulse? Did nearby wavelengths show weaker related emission? Big Ear's record cannot answer all of these questions. A modern telescope would capture far more information. It could divide the signal into much finer frequency channels. It could store raw voltage data. It could examine polarization and sub-second changes. Several observatories could receive an automated alert and point toward the source quickly. The same event occurring today might become explainable. In 1977, it passed through one instrument and left only a narrow trail. The possibility of information hidden inside the signal is especially intriguing. Big Ear measured intensity over intervals lasting several seconds. If the radio source contained rapid pulses, complex modulation, or encoded data changing thousands of times each second, the printout would not preserve that structure clearly. The measurement would average those changes together. A richly organized transmission could therefore appear simply as a strong, narrow signal. But this idea cannot be tested using the surviving data. There is no hidden message available to decode from the characters 6E true. The 6 symbols are only levels of strength. They reveal the outer shape of the event, not the detailed pattern inside it. The WOW signal may have carried information. It may also have carried none. The original instrument did not record enough detail to decide. This illustrates a larger problem in the question: have aliens already answered us? Recognition depends upon the receiver. A signal can arrive while humanity lacks the technology to preserve its meaning. It can pass through an instrument built for another purpose. It can be averaged, filtered, compressed, or discarded. Radio observatories often remove signals that resemble interference because interference is overwhelmingly common. An alien transmission, using a frequency shared with human technology, could be classified as contamination. A highly compressed artificial message might resemble random noise. A broad signal could resemble a natural source. A short pulse could be mistaken for an instrumental glitch. The absence of a recognized answer does not guarantee that no unusual energy has reached Earth. It means no recorded event has survived the full path from detection to independent confirmation. The WOW signal reached the beginning of that path. It looked sufficiently unusual to receive a name. It survived simple dismissal. It inspired repeated searches across several decades. It remains discussed because no ordinary explanation has become universally accepted. But it stopped at the most important stage. It did not repeat. A real answer from another civilization would ideally provide opportunities for confirmation. Perhaps the signal would return at regular intervals. Perhaps its frequency would drift according to the rotation and orbit of a distant planet. Perhaps it would contain mathematical organization. Perhaps multiple observatories would detect it simultaneously. The direction could be traced to one star. The signal might disappear during an eclipse or repeat with the planet's year. Each pattern would connect the transmission to a physical place beyond Earth. A truly deliberate beacon might be designed for discoverability. It could repeat prime numbers. It could occupy several narrow frequencies arranged in a pattern. It could transmit alternating pulses whose structure is difficult to produce through natural physics. The message might begin with simple mathematics before moving toward more complicated information. No famous candidate has shown this complete behavior. The WOW signal produced one smooth pulse. It displayed no known mathematical sequence. Its frequency was suggestive but not uniquely technological. Its direction was celestial but imprecise. Its intensity was exceptional but still physically possible for an astronomical event. Every strength of the candidate is matched by a limitation. This balance has allowed it to remain unresolved for nearly half a century. It has not become weaker through age. It has not become stronger either. A mystery does not accumulate evidence simply because it remains mysterious. Time allows new hypotheses and improved archival analysis. It cannot create a second detection from 9. The most honest description remains that it was a strong, narrow, apparently celestial radio event whose source has not been identified conclusively. It may have been natural. It may have involved interference more complicated than expected. It may have been artificial. Present evidence cannot justify choosing the last possibility as fact. Still, the WOW signal teaches humanity how an answer might begin, not with a spacecraft crossing the sky, not with a voice speaking a human language, not with a complete explanation arriving at once. An answer might begin with a small departure from the background, a narrow line, a rising intensity, a pattern that causes one researcher to stop reading an ordinary page and circle 6 symbols in red. The event would then need to return. Another telescope would need to see it. The signal would have to survive every natural and terrestrial explanation. The WOW signal completed the first moment. It never completed the rest. That is why it remains both famous and insufficient. It is not proof that aliens answered. It is evidence that the universe can produce a signal remarkably similar to the beginning of an answer. Whether the sender was technology, hydrogen, or an event not yet understood, the 72 seconds changed the search. Afterwards, scientists knew exactly how much could be learned from one signal. They also knew how much could remain forever unknown when the signal appeared only once. The next major candidate would behave differently. It would remain present for hours rather than seconds. It would come from the direction of the nearest star beyond the sun. It would drift in frequency as though its source were moving. And for a brief time it would seem that the quiet question left by the WOW signal had returned much closer to home. The next famous candidate arrived from the nearest star beyond the sun. Proxima Centauri rests only a little more than 4 light-years from Earth. It is a small red dwarf belonging to the wider Alpha Centauri system. Around it moves Proxima Centauri b, the closest known exoplanet to Earth. The planet is probably rocky, has a mass similar to Earth's, and completes an orbit in about 11 days. Its orbit lies within the traditional habitable zone. This does not establish that the planet possesses oceans, air, or life. Proxima Centauri is an active star, and its radiation may make atmospheric survival difficult. Yet the planet remains one of astronomy's most compelling nearby worlds because it circles the first star encountered beyond the solar system. A radio signal from almost anywhere would attract scientific attention. A signal apparently associated with Proxima Centauri would feel especially close. 4 light-years is still an extraordinary distance. Light leaving the star requires more than 4 years to arrive. A reply from Earth would require the same time to travel back. But within the scale of the Milky Way, Proxima is a neighbor. It is not separated from Earth by thousands of light-years. It is the next stellar doorway. In April 2019, the Parkes Radio Telescope in Australia observed Proxima Centauri as part of a Breakthrough Listen campaign. The telescope is now known by its indigenous name, Muriang. Its large dish collected radio waves from the direction of the star, while researchers studied activity within the system. The observations covered a broad range of frequencies. At first, nothing within them was publicly known to be exceptional. The data entered an archive. Months later, while researchers were examining the observations for possible technological signals, one narrow line attracted attention. It appeared near 982 MHz. The signal became known as Breakthrough Listen Candidate 1, or, more simply, BLC1. BLC1 contained several qualities expected from a possible distant transmitter. It occupied an extremely narrow range of radio frequencies. The signal also drifted slowly in frequency over time. Its measured drift rate was approximately 0.038 Hz each second. This gentle movement could be consistent with a transmitter located on a rotating or orbiting world. The signal appeared during observations directed toward Proxima Centauri. During the initial filtering, it did not appear clearly within the comparison observations pointed slightly away from the star. It remained present through several on-target scans across roughly 2.5 hours within a longer observing sequence. These features allowed BLC-1 to survive the first scientific filters. It seemed narrow. It seemed persistent. It seemed connected to one direction in the sky. It drifted as though its source and Earth were moving relative to one another. No familiar natural astronomical source was expected to produce exactly that combination easily. For a while, BLC-1 appeared to be one of the strongest modern technosignature candidates, but it was never announced as proof of alien communication. The word candidate remained essential. The first filter does not reveal what a signal is. It only determines whether the signal deserves deeper investigation. BLC-1 had reached the beginning of that investigation. The possibility became especially intriguing because of Proxima b. A transmitter could, in principle, operate from the planet's surface, from a moon, from an orbital structure, or from somewhere else within the system. No evidence showed that any of these objects actually contained technology, yet the known planet provided a physical location around which imagination could gather. The signal did not seem to come from a random empty direction. It appeared to come from a nearby star already known to possess worlds. If BLC-1 had been extraterrestrial, the transmission would not necessarily have been aimed at Earth. It might have been a communication beam crossing the solar system accidentally. It could have been radar, navigation, or a beacon designed for an unknown purpose. Its narrowness might have reflected efficient engineering rather than an intentional greeting. The signal contained no recognized message. There was no mathematical sequence, no image appeared, no language waited to be translated. Like the WOW signal, BLC-1 was interesting because of how its energy was arranged, not because of any meaning identified within it. Yet BLC-1 differed from the WOW signal in one important way. It did not last only 72 seconds. The Parker's observations contained the candidate across several hours. This offered researchers more information. The drift could be traced. The frequency could be measured precisely. The signal's behavior during repeated telescope pointings could be compared. For a brief period, BLC-1 seemed to provide the kind of sustained candidate that the earlier WOW signal had not. But more data can create more opportunities for an ordinary explanation. The same extended observations that made BLC-1 compelling eventually helped reveal its origin. Researchers began by examining the signal itself. They asked whether its drift matched the movement expected from Proxima b, another planet, a satellite, or a transmitter attached to Earth. A signal coming from a distant planet should reflect combinations of orbital and rotational motion. Its drift may change smoothly. Its direction should remain fixed relative to the background stars. A local transmitter may also drift, however. Electronic equipment warms and cools. Oscillators change slightly with time. Satellites move. Signals reflect from aircraft or objects in orbit. The shape of the frequency drift could not identify the source by itself. The candidate had to be compared with everything else recorded by the telescope. This comparison required returning to the full archive. Researchers searched beyond the narrow region surrounding 982 MHz. They examined observations taken when the telescope was not aimed at Proxima Centauri. They looked for other signals with shapes resembling BLC-1. At first, the candidate had appeared isolated. The wider search showed that it was not. Dozens of related signals existed at other frequencies. Some appeared in observations away from Proxima. Their frequency patterns and drift shapes resembled BLC-1 closely. The signals seemed to belong to a family. This family provided the missing clue. The related frequencies showed mathematical relationships consistent with common electronic clock oscillators. Modern electronics contain clocks that regulate timing. Their signals may appear at one fundamental frequency and at related harmonics. When several electronic signals interact inside equipment, they can produce additional frequencies that were not transmitted directly. This is called intermodulation. Two or more ordinary signals combine and generate new products. The effect resembles two ripples crossing upon water and briefly forming another pattern between them. In radio electronics, the new signal may appear narrow and organized. It can drift if the original components drift. It can even align with the telescope's observing schedule in a way that makes it appear connected to a celestial target. Researchers concluded that BLC-1 was an electronically drifting intermodulation product created by local, time-varying radio interference. The signal was technological, but the technology was human. The exact device responsible was not identified with certainty. That was not required to establish the broader explanation. The family of related signals revealed a common terrestrial origin more convincingly than the original candidate revealed a distant one. BLC-1 was no longer one isolated line from Proxima Centauri. It was one member of a group generated through local electronics. The comparison observations had initially failed to reveal this because the interference was intermittent. It appeared during some moments and not others. By coincidence, the pattern aligned with the telescope's cadence. The signal was present during scans of Proxima and absent during several scans away from it. This produced the appearance expected from a source associated with the star. The test itself was sensible. The interference happened to pass it. This is one reason technosignature verification requires several independent filters rather than one. A nearby signal can appear in only one direction if it switches on and off while the telescope moves. It can mimic a celestial source through timing. A drifting electronic oscillator can mimic the relative motion of another planet. A narrow signal is not proof of a transmitter beyond Earth because Earth is already filled with narrow transmitters. Each desirable feature can be reproduced separately by human equipment. Occasionally, several appear together. BLC-1 became a demonstration of coincidence inside a complex radio environment. It did not arrive from the surface of Proxima b. It emerged from interactions much closer to the observatory. The conclusion was strengthened by the failure to detect BLC-1 again. Repeated observations of the Proxima Centauri system did not recover the candidate. An optical search also examined more than 100 high-resolution spectra of Proxima Centauri collected between 2004 and 2019, including observations from the period around the BLC-1 campaign. It found no laser emission associated with the star at the sensitivity examined. Some artificial-looking patterns appeared in the spectra, but their origin was traced to technology within the observing system rather than Proxima Centauri. Radio and optical searches therefore produced no confirmed evidence that the system was transmitting toward Earth. The disappearance of BLC-1 may sound like another promising answer lost. Its scientific value remains substantial. The candidate required a much deeper verification process than most radio detections. Researchers developed and documented a detailed framework for examining future technosignature signals. The process included checking the signal's behavior within on-target and off-target observations, searching wide ranges for related interference, testing harmonic relationships, comparing expected motion, and looking for other explanations throughout the complete dataset. This framework became one of BLC-1's lasting contributions. The candidate did not reveal another civilization. It revealed how terrestrial technology can imitate one with remarkable precision. BLC-1 also demonstrated why secrecy and patience can matter during an investigation. Early information about the candidate reached the public before the full analysis was complete. The words "signal from Proxima Centauri" carried enormous emotional weight. The explanation required months of technical work. By the time the conclusion appeared, the initial possibility had already traveled widely through news reports and online discussion. Science moves more slowly than a headline. A candidate begins with uncertainty. Every test can reduce or increase confidence. The final interpretation may be far less dramatic than the first description. This slow process is not reluctance to accept discovery. It is what allows a discovery to become reliable. A true signal must remain convincing after researchers actively search for reasons to reject it. BLC-1 did not survive that search. This is exactly how the method is supposed to work. A weak process might have announced an alien transmission too early. A careful process found local interference instead. The absence of a discovery was therefore evidence of scientific strength rather than failure. The investigation protected the meaning of any future announcement. The next candidate will be compared against BLC-1. Researchers will ask whether related signals appear at harmonic frequencies. They will search the off-target observations more broadly. They will examine whether local electronics can explain the drift. They will compare the candidate with known clocks, satellites, and navigation bands. They will request rapid confirmation from distant observatories. Every lesson will make the next false positive easier to recognize. It may also make a genuine signal harder to dismiss. Radio frequency interference is one of the deepest practical challenges in SETI. The quietest astronomical observatories are never completely separated from civilization. Satellites now cross the sky in enormous numbers. Aircraft pass above the horizon. Navigation systems transmit continuously. Ground-based radars release powerful pulses. Phones, computers, vehicles, power supplies, and digital devices generate unintended emission. Some signals travel directly into the telescope. Others reflect from objects in the atmosphere or space. Still others are produced inside the observatory's own electronics. The telescope is attempting to detect distant technology while standing within the electromagnetic glow of Earth's technology. This situation creates an unusual reversal. A successful technological civilization is surrounded by the very evidence that makes searching for another technological civilization difficult. The more active Earth becomes in radio, the more crowded the listening environment becomes. Protected radio astronomy bands provide some relief. Remote locations reduce nearby transmission. Filtering software removes familiar patterns. But no location on Earth is perfectly silent. Even a radio observatory in a sparsely populated landscape can receive signals from orbit. The sky itself carries human machinery. A future search may increasingly depend on observatories located beyond Earth. The far side of the Moon is shielded from much of the radio emission generated near the planet. A telescope placed there could listen within frequency ranges that Earth's atmosphere or technology makes difficult to use. The lunar landscape would block direct radio noise from Earth. The Moon would become a quiet wall between the receiver and human civilization. Such instruments remain technically challenging. They would need construction, power, communication, and maintenance across a distant surface. Yet the scientific advantage could be extraordinary. A lunar radio telescope might hear portions of the spectrum that have never been observed cleanly. Until then, Earth-based observatories must separate the galaxy from the planet beneath them. They do this through repetition. A human signal often appears from many directions. A celestial signal follows one source. Interference may vary from one observatory to another. A distant transmission should be recorded independently by instruments separated across Earth. A satellite may move rapidly relative to the stars. A transmitter on another world should remain tied to its planetary system. Each comparison turns location into evidence. A real answer would ideally become stronger as the number of observing sites increased. Imagine a narrow signal appearing during an observation of one nearby star. The first telescope alerts others automatically. A second instrument on another continent points toward the same coordinates. Then a third. All detect the signal at the time predicted after accounting for their locations. The signal drifts consistently. It disappears when each telescope points away. It returns when the star is observed again. A satellite database shows no object crossing the region. The frequency avoids known terrestrial services. No harmonic family appears elsewhere in the data. The signal repeats the following night. Its timing matches the rotation or orbit of a planet. This would not yet reveal the sender's appearance, intentions, or language, but it would be unlike BLC-1 in the way that matters most. The evidence would follow the star through independent instruments. The signal would no longer depend upon one observatory's local environment. Even stronger evidence could come from modulation. A transmitter may vary its amplitude, frequency, polarization, or pulse timing. These changes can carry information. Natural objects also vary, sometimes regularly, but a sufficiently elaborate mathematical structure could become difficult to explain without design. Prime numbers are often imagined because they are independent of human language. A sequence containing 2 pulses, then 3, then 5, then 7, could suggest deliberate organization. Geometric relationships might offer another common foundation. Yet another intelligence may not choose symbols that human researchers expect. Its message could use a mathematical system organized differently. Its transmission may be compressed until it resembles noise. It may contain a simple beacon rather than a detailed message. Artificiality may be recognized long before meaning. BLC-1 contained no identified modulation of this kind. Its value came from narrowness, direction, persistence, and drift. When its wider radio family appeared, those features became explainable through electronics. A genuine answer would need some property that survives the discovery of every related pattern. It would become more isolated from Earth. As the investigation expanded, BLC-1 became more connected to Earth instead. This movement from apparently celestial to demonstrably local is one of the clearest ways to understand the result. At first, the candidate seemed attached to Proxima Centauri. Then related signals appeared in the observatory's broader data. Each relationship pulled the source closer. Harmonic frequencies connected it to electronic clocks. Intermodulation connected it to interacting transmitters. Its timing connected it to intermittent local interference. The signal's mystery did not vanish all at once. It was gradually drawn back into the technological environment already surrounding the telescope. The process is almost the reverse of confirmation. A genuine extraterrestrial candidate should move outward under investigation. Its direction should become more precise. Its connection to a star or planet should become stronger. Independent telescopes should reproduce it. Natural and terrestrial explanations should fall away. BLC-1 moved inward. The broader the investigation became, the more terrestrial it appeared. This distinction may guide every future search. An extraordinary signal should not remain extraordinary, only within one carefully selected piece of data. It should become more extraordinary when the full context is examined. The BLC-1 story also carries a subtler possibility. If a real signal resembles interference closely, it may be rejected. An extraterrestrial civilization could transmit near 982 MHz. Its frequency might overlap with terrestrial navigation bands by coincidence. Its signal could drift similarly to an electronic oscillator. It might appear only during on-target scans and fail to repeat. In such a case, researchers could reach the correct cautious conclusion that the available evidence does not justify an extraterrestrial claim, while the signal itself was genuinely distant. Science cannot eliminate this possibility from every one-time event. The purpose of verification is not to identify every true source with perfect certainty. It is to establish which claims the evidence can support. A real but non-repeating signal may pass unrecognized. That is one cost of avoiding false discovery. The answer is not to lower the standard. It is to expand observation. More telescopes, broader frequency coverage, faster alerts, longer monitoring, better interference databases, observatories in quieter locations. The aim is to make the next real signal provide enough evidence that caution and discovery point toward the same conclusion. BLC-1 may therefore represent an answer to a different question. Not whether aliens have contacted Earth, but whether humanity is technically prepared to recognize contact. The candidate showed that modern systems can identify a subtle narrowband line within immense datasets. They can notice drift. They can isolate signals that initially follow a celestial source. They can organize months of verification and publish the complete reasoning. The search is capable of taking a candidate seriously without becoming attached to it. That balance will be essential if a stronger event appears. For several hours in 2019, one radio line seemed to occupy the narrow boundary between Earth and Proxima Centauri. Its frequency moved gently. Its source appeared fixed near the closest stellar neighbor. A planet waited within that system. The shape of the observation allowed a remarkable possibility to remain open. Then the wider data revealed many quieter companions. The candidate became one pattern among a family of human-made signals. The apparent answer returned home. Nothing within this conclusion makes Proxima Centauri less interesting. The star remains nearby. Proxima b remains a compelling rocky world whose atmosphere and surface are largely unknown. Future telescopes may study the system with greater sensitivity. New radio surveys may return many times. Optical observatories may search for laser pulses. Planetary imaging may eventually reveal more about the worlds circling the star. BLC-1 was not their voice. That does not mean the system has nothing to say. It means one signal has been understood well enough to remove it from the list. The search continues with a clearer method. The WOW signal remains unexplained because too little information survived. BLC-1 became explained because much more information was available. One mystery persisted through absence. The other dissolved through context. Together they show the two possible fates of an unusual signal. It may vanish before science can understand it, or it may remain long enough for its ordinary connections to emerge. A genuine answer must follow a third path. It must remain long enough to be studied and become less ordinary with every new observation. Before humanity could recognize an artificial signal, it first had to learn how strange natural radio signals could become. In 1967, graduate student Jocelyn Bell Burnell was studying observations from a newly constructed radio telescope near Cambridge, England. The instrument had been designed to examine quasars, but Bell noticed a small irregular mark appearing repeatedly within long paper records. The source produced pulses separated by roughly 1.3 seconds, with a regularity that initially seemed difficult to explain through known astronomy. The signal did not resemble the broader, less orderly radio emission usually associated with stars and galaxies. It resembled a clock. The pulses returned so precisely that Bell and her supervisor, Anthony Hewish, briefly considered whether the source might be artificial. The object was given the private nickname LGM-1, referring playfully to little green men. The name did not represent an announcement of alien contact. It reflected the honest uncertainty surrounding a pattern that looked more engineered than anything known in the radio sky at that time. The possibility did not last long. Bell discovered additional pulsing sources in different parts of the sky. It became increasingly unlikely that several unrelated civilizations had begun transmitting nearly identical signals toward Earth at the same moment. A natural explanation emerged. The sources were rotating neutron stars. A neutron star forms when the core of a massive star collapses. More mass than the Sun can become compressed into an object only about as wide as a city. The star's magnetic field becomes extraordinarily strong, and its rotation can become extremely rapid. Radiation streams outward from regions near the magnetic poles. The magnetic axis is not always aligned with the rotation axis. As the neutron star spins, the beams sweep through space like the light from a turning lighthouse. Earth detects a pulse whenever one beam crosses the line of sight. The star is not repeatedly switching itself on and off. Its radiation remains focused into a moving beam, appearing briefly during each rotation. These objects became known as pulsars. Some complete a rotation in a little more than a second. Others rotate dozens or hundreds of times each second. The pulsar inside the Crab Nebula turns approximately 30 times per second, producing regular flashes across radio, optical, X-ray, and gamma-ray wavelengths. A signal that first seemed almost too precise for nature became evidence of one of nature's most extreme objects. The explanation was not less extraordinary than the alien possibility. It revealed matter compressed beyond ordinary experience, magnetic fields shaping particles near the speed of light, and stellar remnants turning with the regularity of cosmic clocks. The apparent message was not communication. It was rotation made visible. Pulsars provided an enduring lesson for the search for alien answers. Regularity is not enough. Repetition is not enough. Even a pattern precise enough to resemble machinery may emerge from gravity, magnetism, and motion. Nature does not always produce disorder. Under the correct physical conditions, it creates rhythms more stable than many human instruments. This lesson became especially important because regular pulses are among the patterns researchers expect from deliberate beacons. A civilization attempting to attract attention might send repeated bursts. The intervals could carry numbers or mathematical relationships. But a neutron star also sends repeated bursts. The distinction must be found within the details. A pulsar's period changes slowly as the star loses rotational energy. Its pulses appear across characteristic ranges of the electromagnetic spectrum. Its position may coincide with a supernova remnant. Its frequency structure and polarization follow patterns produced by plasma and magnetic fields. A technological beacon might show a different kind of organization. It could contain deliberate modulation. It could change according to a mathematical sequence rather than a rotating object's steady period. Its signal might occupy an exceptionally narrow radio channel or encode information too elaborate for known stellar physics. The discovery of pulsars therefore did not weaken SETI. It improved the definition of artificiality. A candidate had to be more than surprising. It had to remain unnatural after astronomers understood the full behavior of the source. Pulsars later became valuable tools rather than sources of confusion. Their timing allows researchers to study matter between the stars, test gravity, map neutron star interiors, and search for the subtle effects of gravitational waves. NASA's NICE mission has used X-ray pulses to investigate the size and structure of neutron stars. while pulsar timing projects compare signals from many objects across the sky. The false beginning became an instrument for deeper science. A signal once associated briefly with alien intelligence now helps measure the universe itself. Several decades later, radio astronomy encountered another class of signals that seemed equally difficult to understand. They were not steady clocks. They were extremely brief flashes. Fast radio bursts, usually shortened to FRBs, last only milliseconds, yet some release tremendous amounts of radio energy. Most arrive from galaxies far beyond the Milky Way. Their short durations and great distances make them among the most intense transient radio events known. The first recognized example was found in archival telescope observations. Later searches discovered many more. Some FRBs appeared only once. Others repeated from the same location, sometimes producing clusters of bursts separated by quiet intervals. Their signals had traveled through clouds of ionized material before reaching Earth. Lower radio frequencies arrived slightly later than higher frequencies, allowing astronomers to estimate how much material the signal crossed during its journey. The dispersion helped show that many FRBs came from far beyond the Milky Way, rather than from nearby interference. A new cosmic population had appeared. At first, almost every explanation remained open. The bursts might come from collapsing stars, merging compact objects, black holes, neutron stars, or unfamiliar plasma processes. Technology also entered public speculation. A sufficiently advanced civilization might create powerful radio pulses deliberately. Some imagined communication beacons, others considered propulsion systems using immense beams of energy. The brief and energetic nature of FRBs made them resemble the kind of dramatic signal that an artificial transmitter could produce. But resemblance alone did not connect the bursts to intelligence. Their distribution across the sky created an immediate challenge for a technological interpretation. FRBs appeared from many galaxies and enormous distances. If they were artificial, many civilizations would need to produce broadly similar bursts. A natural mechanism common to certain stellar environments offered a simpler starting point. The search therefore focused upon finding the physical objects associated with the signals. Repeating FRBs were especially useful. A one-time burst provides only one moment of data. A repeating source can be observed again. Telescopes can localize it more precisely, study its environment, compare its bursts, and search for emission at other wavelengths. One important repeater, FRB 121, Li02, produced many detectable events. Machine learning analysis later identified 72 additional bursts within observations that had already been collected, showing how unusual signals can remain hidden until improved software examines the same data differently. The bursts did not repeat like a simple clock. Their timing was irregular, their shapes varied. Some contained smaller subbursts that drifted through frequency. Other repeating FRBs displayed their own activity cycles and spectral structures. The variation made the signals scientifically rich. It also made them less like one obvious message. No repeating FRB has revealed confirmed mathematical encoding, language, or behavior requiring a technological source. Their patterns instead offered clues about energetic objects surrounded by magnetized plasma. The strongest natural connection arrived in April 20. A magnetar inside the Milky Way, known as SGR 1935+2154, entered a period of intense activity. Magnetars are neutron stars possessing exceptionally powerful magnetic fields. Like ordinary pulsars, they are compact remnants of massive stars, but their magnetic energy can produce sudden X-ray and gamma-ray outbursts. During the 2020 activity, telescopes detected a powerful radio flash at the same time as high-energy emission from the magnetar. It was the first fast radio burst-like event recorded from within the Milky Way. The burst was less energetic than many distant FRBs, but its relationship with the magnetar was clear enough to demonstrate something essential. Magnetars can produce fast radio bursts. The discovery did not explain every FRB automatically. Different sources may arise from different mechanisms. Even among magnetars, the exact process that converts magnetic energy into a bright millisecond radio pulse remains an active area of research. Some bursts may be associated with sudden changes in magnetic fields. Others may involve shock waves moving through material surrounding the star. Several physical pathways may produce related radio events. But the 2020 observation crossed an important threshold. An object known to exist in nature had created the same broad type of signal that once seemed mysterious across other galaxies. The technological explanation was no longer needed to show that such bursts were physically possible. Nature had produced one close enough for multiple observatories to connect the radio flash with its high-energy source. A supposed cosmic message became another expression of a neutron star. Once again, the answer was not less remarkable because it was natural. A magnetar's magnetic field can store and release energy on a scale beyond anything built by humanity. Its crust can shift, its magnetosphere can rearrange. A disturbance lasting only a fraction of a second can produce radiation detectable across the galaxy. The signal contains no deliberate greeting. It contains a record of matter and magnetism under extraordinary conditions. Fast radio bursts also revealed how easily the word repeating can be misunderstood. A repeating signal is valuable because it allows confirmation, but repetition by itself does not indicate intention. Lightning repeats. Volcanoes erupt more than once. Stars flare. Pulsars pulse. Magnetars produce storms of bursts. A machine can repeat, but so can a physical system returning to similar conditions. The artificial interpretation becomes stronger only when repetition contains organization that known natural mechanisms cannot reproduce. A beacon might transmit at exact scheduled intervals unrelated to orbital or rotational motion. It might arrange pulses into prime numbers. It could switch among frequencies in a deliberate geometric pattern. It might transmit a sequence that becomes more complicated while preserving a recognizable mathematical grammar. FRBs have displayed rich structures. They have not displayed confirmed evidence of such communication. Some FRBs occur in clusters and then become quiet. Some repeat unpredictably. Their spectral properties vary from burst to burst. These behaviors are consistent with energetic astrophysical environments whose internal conditions change. Astronomers continue to investigate them because the natural mechanisms are not fully understood, not because the sources require alien transmitters. The distinction between unexplained and artificial becomes especially important here. An FRB may contain features that have no complete model. That does not place technology at the top of the remaining possibilities. A magnetar can be identified as the broad source class, while the exact mechanism of each pulse remains unknown. Science often understands an event in layers. A storm may be known to come from a magnetar before every detail of its magnetic field can be reconstructed. A volcanic eruption can be identified without predicting the motion of every particle of ash. Uncertainty within the natural explanation does not make an artificial explanation equally supported. Positive evidence for design is still required. This principle protects the search from turning every new astronomical phenomenon into a hidden message. The universe continually presents events outside existing categories. The first pulsar looked artificial before neutron star lighthouse beams were understood. The first fast radio burst looked unlike familiar radio sources before magnetars were connected to at least some of them. A future observation may seem even stranger. It may come from an object no theory currently predicts. SETI must remain open to technology without treating the absence of a natural explanation as the presence of one. The search therefore asks two questions in parallel. Can nature make this? And does the signal contain something nature would not be expected to make? The first question expands as astronomy discovers new objects. The second becomes more demanding. A real message must survive both. There is also a deeper possibility hidden within natural signals. Another civilization could use them deliberately. A society might modify a pulsar's pulses or place a transmitter near a powerful natural radio source. It could use an existing cosmic beacon as a landmark. A regular pulsar would already attract astronomers' attention. Small artificial changes imposed upon its timing might become visible to careful observers. This idea remains speculative. No pulsar has shown confirmed evidence of such manipulation, but it illustrates why artificiality may not always appear as an entirely separate signal. Technology can hide within nature. Human communication already uses carriers. A radio station begins with a predictable wave and adds information through changes in amplitude, frequency, or phase. An alien civilization might use a natural astronomical source in a related way. The challenge would be identifying modulation that cannot arise from the source itself, its orbit, its plasma environment, or intervening material. Researchers would need long records. They would need to predict the natural pulse precisely and identify deviations containing persistent structure. Pulsar timing is now accurate enough to measure extraordinarily small changes. So far, those changes have revealed planets, stellar companions, gravitational effects, and properties of interstellar material rather than messages. NASA notes that the first confirmed exoplanets were found around a pulsar, detected through subtle variations in its timing. This discovery adds another gentle reversal. Pulsars first imitated alien transmitters. Later, one became the first star known to host confirmed planets beyond the solar system. The signal was not a message from inhabitants of those planets, but its timing revealed that worlds existed there. An apparent artificial beacon became a natural lighthouse, and the lighthouse became a tool for discovering distant planets. Radio astronomy often advances through these transformations. An unknown pattern begins as mystery. Repeated observations uncover a source. The source becomes a new type of natural object. That object then becomes a tool for studying other parts of the universe. Nothing is lost when the alien explanation fades. The mystery changes shape. It becomes understanding. Fast radio bursts are undergoing the same process. As more are localized, astronomers can study the galaxies and stellar environments that produce them. The signals also pass through vast regions of space, carrying information about otherwise difficult to observe material between galaxies. The amount of dispersion reveals electrons along the path. Polarization provides clues about magnetic fields. A burst lasting milliseconds can therefore describe not only its source, but the space it crossed. What appeared at first like a possible artificial flash becomes a probe of cosmic structure. Modern SETI instruments sometimes study FRBs and technological signals with the same telescopes. This is not a contradiction. Both searches require fast processing, broad bandwidth, sensitivity, and the ability to identify brief events within large datasets. The Allen Telescope Array, for example, participates in SETI research while also observing repeating FRBs. New artificial intelligence systems are being developed to detect bursts rapidly and enable networks of telescopes to respond in real time. The methods support one another. A system trained to recognize natural transients becomes better at distinguishing them from possible technosignatures. A search for artificial pulses may discover an unusual natural event. A telescope does not need to know in advance which kind of signal will arrive. It listens. The classification comes later. This shared approach reflects the central uncertainty of any first detection. A genuine alien transmission would begin as an astronomical event. It would enter an antenna as electromagnetic energy. Software would compare it with noise, interference, stars, pulsars, magnetars, and known satellites. Only after the natural and human categories failed would the technological category become persuasive. The signal would not arrive carrying a label. Its origin would emerge from behavior. This is why the history of pulsars and FRBs is part of the history of SETI, even though neither became evidence of alien intelligence. They define the background against which an answer must be recognized. Before pulsars, an exact repeating pulse seemed highly artificial. After pulsars, researchers understood that rotating neutron stars could produce one. Before FRBs, a millisecond flash from another galaxy seemed nearly beyond natural explanation. After the magnetar event of 2020, nature had demonstrated a mechanism capable of producing at least part of the population. Every natural discovery removes one simple route to certainty. It also makes the final standard stronger. A candidate can no longer be called artificial merely because it pulses. It cannot be called artificial merely because it releases enormous energy or comes from another galaxy. It must contain organization beyond the natural rhythms now known. Perhaps this organization will appear through information theory. A message may have statistical properties unlike stellar noise. It may contain layers of redundancy designed to survive interstellar distortion. Its structure could become more comprehensible as longer portions are received. Mathematical patterns might repeat at several scales. The transmission may respond after Earth sends a signal, though the light travel delay could make this test take years or centuries. Direction will matter. A natural transient may occur once within a galaxy. A transmitter associated with a planet should remain tied to that system. Its Doppler motion could trace the planet's orbit or rotation. Repeated observations may reveal periods corresponding to a day or year. If the transmitter operates from a moving spacecraft, its acceleration could follow a deliberate trajectory. A signal that carries information and moves consistently with one known world would be far harder to explain through a neutron star. Independent confirmation will matter equally. A magnetar burst can be seen by several telescopes, so multiple detection alone does not prove technology. But it establishes that the event is celestial rather than local interference. Astronomers can then compare radio, optical, X-ray, and gamma-ray observations. A natural source may reveal an energetic counterpart. A technological source might remain narrow and organized without the broader high-energy activity expected from a stellar explosion or magnetar flare. Context transforms the signal. One line in one telescope creates possibility. A multi-wavelength history creates understanding. The first confirmed answer may therefore emerge partly through the absence of natural context. A narrow radio transmission repeats from a quiet star. No flare accompanies it. No neutron star occupies the location. No known plasma process explains the bandwidth. The signal drifts with a planet. Its internal structure contains mathematics. Separate observatories detect the same sequence. Each feature removes another natural alternative. Artificiality would not be declared because the signal seemed strange. It would be declared because the complete pattern behaved like communication. Until such a pattern appears, pulsars and fast radio bursts remain gentle warnings against impatience. The sky is filled with apparent voices. Many belong to rotating stars. Others belong to magnetic outbursts. Some last for milliseconds. Some continue for millions of years. Their rhythms can seem intentional because the laws of physics are capable of producing precision. There is no disappointment in this. A pulsar is a star's collapsed heart turning like a beacon. A fast radio burst is a flash that can cross billions of light years and arrive within less time than a human blink. These are not answers from alien civilizations. They are answers from the universe itself. They reveal that the radio sky is neither empty nor simple. It contains clocks, storms, flashes, echoes, and signals shaped by matter between galaxies. Any artificial message must travel through this living background of natural radiation. It must be distinct enough to rise above it. The discovery of pulsars once suggested that another intelligence might have sent a perfectly regular pulse. The discovery of magnetar-generated bursts later suggested that a distant civilization might have sent an enormous flash. Both possibilities returned to nature, but each return prepared the search for something more convincing. The next genuine candidate will be compared with rotating neutron stars. It will be compared with magnetars, plasma, orbital motion, and every known class of transient. If it survives, its survival will mean more because of the signals that came before. Nature has already answered in many unexpected voices. The remaining question is whether one voice will someday contain intention. An answer from another civilization may not arrive through radio at all. It may arrive as light. A brief flash could appear beside a distant star. It might last for only a billionth of a second, yet contain enough concentrated energy to stand above the star's ordinary glow. Or the signal could remain steady. A razor-thin line of one precise color might sit inside a stellar spectrum, brighter and narrower than anything expected from the star itself. Human eyes would probably never notice it. The light would be collected by a telescope, divided into wavelengths, and examined by software searching for patterns that nature does not usually create. This is optical SETI. It asks whether another civilization might use visible or near-infrared lasers to communicate across interstellar space. Radio waves have dominated SETI for much of its history, partly because radio technology matured early and because certain radio frequencies pass efficiently through interstellar material and Earth's atmosphere. But lasers offer their own advantages. They can be directed with extraordinary precision. They can concentrate large amounts of energy into a narrow beam. They can carry information rapidly, and their light can be confined to an extremely small range of wavelengths, producing a spectral line that may stand apart from ordinary starlight. A laser does not spread evenly in every direction. Its beam slowly widens as it travels, but far less dramatically than an ordinary lamp or broadcast antenna. A civilization that knows Earth's position could direct a pulse toward the solar system. Most of the energy would remain inside a relatively narrow cone. When that cone reached Earth, a sufficiently sensitive telescope might detect the pulse even after it had crossed many light years. The beam could outshine the civilization's own star for one tiny moment at one chosen wavelength. Not because the laser released more total energy than the star. The star radiates across every direction and across a broad spectrum. The laser concentrates its power into one direction, one color, and one brief interval. It is the difference between a glowing room and a focused flashlight, seen from far away. The room releases much more total light. The flashlight remains easier to notice because its energy is aimed. A distant civilization might use this property deliberately. A pulse could function as a beacon. It might repeat every few seconds. It could contain groups of flashes arranged into numbers. It might first announce its presence with simple patterns, then transmit more complicated information after attention had been attracted. The signal could also be ordinary communication never intended for Earth. Two settlements within another planetary system might exchange laser beams. A spacecraft might communicate with its home world. An observatory could send data across the system. If Earth happened to cross the narrow beam, a telescope might intercept a fragment. The light would become an accidental answer. It would reveal technology, without revealing whether the sender knew humanity existed. Optical communication is not only an imagined alien technology. Human engineers already use lasers to transmit information. Laser communication can carry high data rates between satellites and spacecraft, while using narrower beams than many radio systems. This makes it efficient, but it also makes interception difficult. A receiver must be positioned very close to the beam's intended path. The same limitation would apply to an interstellar transmission. A laser message may pass through the galaxy like a thin thread. Earth must cross that thread at the correct moment. Even a powerful civilization could transmit continuously while remaining invisible from most directions. Radio searches often examine one narrow piece of the sky and one range of frequencies at a time. Optical searches face a similar challenge, but with an additional problem. A laser pulse can be extremely brief. A telescope may observe the correct star 1 minute before the pulse arrives and then turn elsewhere. The message crosses Earth while no suitable instrument is watching. The entire event ends before a person could blink. This possibility changes the meaning of silence. The absence of a detected optical signal does not necessarily mean no lasers exist. It may mean that the search has not yet matched the beam in position, wavelength, and time. The space of possibilities is enormous. There are hundreds of billions of stars in the Milky Way. Each can be observed across many wavelengths. Signals may last from fractions of a nanosecond to years. They may repeat regularly, irregularly, or never. They may be aimed directly at Earth or pass nearby by chance. Humanity has explored only a small portion of this vast search space. One optical strategy focuses upon extremely short pulses. A nanosecond is 1/1000th of a second. Within such a small interval, the ordinary light from a star contributes only a limited number of photons to a detector. A sufficiently strong laser pulse can therefore create a sudden cluster of photons arriving almost simultaneously. The cluster appears unlike the smoother flow of starlight. The telescope does not need to read a message during the first detection. It only needs to notice that too many photons arrived at once. Early optical SETI systems often used several detectors observing the same star. A real pulse from the sky should reach all detectors almost simultaneously. A random electronic fluctuation inside one detector would probably not appear in the others. This coincidence test helps separate celestial flashes from instrumental noise. Later instruments expanded the idea with faster electronics, larger fields of view, and more sophisticated cameras. SETI is designed to survey very broad regions of the visible and near-infrared sky for short optical events. Rather than studying only one star at a time, the project uses many compact instruments to watch large portions of the sky and search for both possible technosignatures and natural astronomical transients. The design resembles a collection of many watchful eyes. Each instrument covers a wide area. Together they can observe thousands of stars at once. A short pulse no longer needs to arrive from one pre-selected target. It can occur almost anywhere inside the field. This increases the chance of catching unexpected events. It also increases the amount of ordinary activity that must be understood. Meteors cross the atmosphere. Satellites reflect sunlight. Aircraft lights flash. Cosmic rays strike detectors. Stars flare. Electronic systems produce false pulses. A wide-field instrument sees a much more active sky than one tightly focused telescope. The search therefore relies upon geometry and repetition. A nearby meteor may appear to move across several cameras. A satellite follows a path. A cosmic ray may affect only one sensor. A truly distant flash appears fixed against the stars and should be detected consistently by instruments viewing the same region from different positions. Observatories separated by many kilometers provide a powerful test. A local event may look different from each location. A flash arriving from beyond the solar system reaches both observatories from nearly the same celestial direction. This is one reason optical SETI networks are designed with overlapping coverage. Independent stations can compare detections and reject events produced near one instrument. Laser SETI follows another wide-field approach. Its instruments spread incoming light into spectra, so that each star produces a small streak of colors. Ordinary starlight contains many wavelengths. A monochromatic laser flash would appear concentrated at one narrow color within that streak. The system is designed to monitor large portions of the sky continuously, rather than visiting one target for a short scheduled observation. The project has been expanding through a network of stations intended to provide overlapping coverage and eventually broader continuous monitoring. Continuous watching matters because a transmission may not repeat. The WOW signal demonstrated how frustrating a single brief radio event can become. An optical pulse could be even shorter. A telescope that records only a few exposures each night might miss it entirely. A network observing repeatedly creates more chances to catch the moment. It also provides information before and after the flash. Researchers can ask whether a satellite crossed the area. They can compare weather conditions. They can search for a meteor or natural transient. They can examine whether the same location flashes again. The event becomes part of a timeline rather than one isolated point. There is another optical method that does not search for brief pulses. It searches for persistent laser lines hidden inside the spectrum of a star. When astronomers study starlight with a spectrograph, they separate the light into a finely detailed rainbow. Dark and bright lines appear at specific wavelengths. These lines come from atoms and molecules absorbing or emitting light. Hydrogen, sodium, calcium, oxygen, and many other substances each leave recognizable patterns. A laser can create a very different line. Its wavelength may be extraordinarily narrow. Instead of being broadened by hot-moving gas, the emission could occupy only a tiny part of the spectrum. If the laser were powerful enough and aimed toward Earth, it might appear as a bright spike rising above the star's natural spectrum. The spike could remain visible for minutes, hours, or years. This type of signal would be easier to revisit than a nanosecond pulse. A telescope could return to the star and search for the same wavelength. Another observatory could examine it independently. The line's motion could be tracked. If it came from a planet orbiting the star, its wavelength might shift slightly as the planet moved toward and away from Earth. This repeating Doppler pattern could connect the light to one world. Breakthrough. LISTEN researchers have developed automated searches for narrow optical laser emission within high-resolution stellar spectra. One analysis examined 1,983 spectra of 388 stars collected with the automated planet finder. It found no convincing extraterrestrial laser candidate in that sample, while demonstrating sensitivity to powerful directed lasers over nearby interstellar distances. A null result does not mean that none of the stars host technology. It means that no laser matching the searched properties was detected during those observations. The transmitter may have been off. Its beam may have pointed elsewhere. Its wavelength may have fallen outside the instrument's range. It may have been weaker than the detection threshold. It might have pulsed between exposures. Or no transmitter may exist there at all. Each search excludes only a defined region of possibility. The language of scientific results therefore remains precise. Researchers do not say that a star contains no civilization. They say that no signal stronger than a certain limit was found within a certain wavelength range during a certain period. These limits accumulate. As more stars are observed, more of the search space becomes measured. A civilization deliberately attempting contact could make the problem easier. It might choose a wavelength associated with a universal physical feature. Radio SETI often considers the hydrogen line because any radio-astronomical civilization would probably recognize it. Optical communication could use atomic transitions, common astronomical spectral lines, or mathematically chosen wavelengths. A transmitter might pulse when an exoplanet passes in front of its star from Earth's perspective. The transit would provide a natural time marker. Earth astronomers already watch the system during that event. A civilization familiar with our observing habits could use the moment to attract attention. It could send a pulse immediately before, during, or after the transit. The planet itself would act like a cosmic appointment. The same idea can be reversed. A civilization observing the solar system may notice Earth passing in front of the Sun. From its position, the planet would create a tiny regular dip in sunlight. It could infer Earth's size and orbit. It might detect oxygen, water vapor, methane, or industrial gases in our atmosphere. If it chose to communicate, it could send a laser toward Earth at the exact time it expected human astronomers to be observing its own world. The geometry would create a shared reference. No calendar or spoken language would be needed. Both civilizations would understand orbital motion. This remains hypothetical. No confirmed laser pulse has been received during an exoplanet transit. But the method illustrates how contact could be timed intelligently, rather than transmitted continuously. A civilization does not need to use unlimited energy. It only needs to know where attention is likely to be. Another possibility is synchronization with dramatic astronomical events. A supernova, nova, or bright stellar flare attracts telescopes from across a planet. An artificial pulse transmitted near the event could arrive while many observatories are already watching. The sender might place the pulse slightly before or after the natural explosion, creating a pattern unlikely to be accidental. This concept is sometimes called signal synchronization. Nature provides the clock. Technology adds the mark, yet this strategy requires the sender to predict how the event appears from Earth and to know the distance accurately enough to time the pulse. For a supernova, this may be difficult unless the civilization controls an artificial event or observes a predictable repeating phenomenon. Planetary transits, binary star eclipses, and pulsars offer more regular timing. A message could also be spread across many stars. Instead of one bright beacon, multiple lasers could flash in a geometric pattern visible across the sky. The sequence might trace a line, circle, or mathematical figure. Each individual flash could resemble a natural transient. Together, their arrangement would suggest coordination. Wide-field surveys are especially valuable for this possibility because they examine relationships across large regions rather than treating every star independently. Time domain SETI research explores how spatial and temporal patterns across many observations could reveal technology that would be missed by traditional single-target searches. A coordinated pattern could be slow. One star flashes tonight, another flashes tomorrow. A third follows 1 week later. The sequence may not become visible until years of data are combined. Astronomical archives could again contain an answer that was not recognized at the moment of arrival. Software would need to search not only for unusual brightness, but for relationships across time and direction. The possible message might exist between events rather than inside one event. This resembles a constellation drawn deliberately through light. Humanity already creates artificial patterns visible from space. Cities illuminate coastlines. Satellites move in organized groups. Laser-ranging stations send pulses toward spacecraft and reflectors on the moon. From nearby astronomical distances, most of these signals would be extremely difficult to detect, but they show that technology does not always appear as one message. It can appear as organization across a landscape or system. An extraterrestrial observer might recognize Earth through patterns of illumination before decoding a single sentence. The search for optical answers therefore overlaps with the broader search for technosignatures. A laser is only one way technology can alter light. Artificial structures may block starlight. Large groups of satellites could change a planet's brightness slightly. Powerful propulsion beams might create short optical or infrared flashes. Industrial processes may emit spectral lines that do not match ordinary planetary chemistry. A civilization using enormous amounts of energy could release waste heat visible in infrared wavelengths. Technosignatures include all observable evidence that technology has shaped matter or radiation, not only deliberate communications. This leads to a quiet change in the original question. Have aliens already answered us? Perhaps an answer does not require a reply. A civilization may never have heard Earth's transmissions. It may have existed millions of years before humans evolved. Its light could be arriving now. A persistent laser beacon might continue operating after its creators disappeared. An automated system could transmit for geological timescales. Technology can, in principle, outlive biology. A machine may remain in orbit. A transmitter may continue drawing energy from a star. A structure may persist as a silhouette. An answer might come from the past. The sender does not need to be listening anymore. This possibility distinguishes technosignatures from many biological signs. A biosphere depends upon continuing life. Atmospheric oxygen can decline after organisms vanish. Vegetation disappears, but certain artifacts may survive. A probe beacon or altered planetary surface could remain after the civilization that built it has ended. The galaxy may contain technological fossils. Light could carry their final evidence across time. A telescope examining a star today sees that star in the past. If it lies 1,000 light-years away, its light began traveling toward Earth 1,000 years ago. A detected laser would reveal the transmitter as it existed then. By the time humanity received it, the civilization might have changed completely. It may have expanded. It may have become quiet. It may no longer exist. Communication across the galaxy always contains this temporal distance. A signal is both a message and an archaeological object. It preserves one moment of another world. Lasers appear suitable for long-distance communication, but they also face physical challenges. Interstellar dust can absorb and scatter shorter wavelengths. Earth's atmosphere distorts incoming light. Clouds can block it entirely. Turbulence makes stars shimmer and spreads their images. A civilization choosing a wavelength would need to consider the material between stars and the properties of the receiving planet. Near-infrared light may pass through some dust more effectively than visible light. Space-based receivers would avoid clouds and much atmospheric distortion. The best wavelength depends upon distance, direction, available technology, and the desired beam width. A sender may choose a wavelength that human searchers have not examined deeply. The signal could arrive in ultraviolet, infrared, X-rays, or another region of the electromagnetic spectrum. Optical SETI is therefore one section of a much wider search. The word optical often includes visible and nearby infrared wavelengths because related instruments can study both. Other high-energy searches ask whether advanced technology could produce gamma-ray or X-ray patterns. These ideas are more speculative and often face greater natural backgrounds. Stars, black holes, and neutron stars are powerful emitters. Technology must distinguish itself from some of the most energetic objects in the universe. A laser signal has one advantage here: coherence. Laser photons share a highly organized relationship. They occupy narrow wavelengths and phases. Natural light is usually less ordered, but astronomical instruments do not always preserve enough information to measure coherence directly across interstellar distances. Researchers often search instead for its consequences: narrow spectral lines, short pulses, high directionality, and unusual brightness. Each feature can have natural or instrumental imitations. The complete pattern matters. A brief flash may be caused by a meteor. A narrow line may be produced by an atom. A sudden camera event may be created by a cosmic ray. A glint may come from a satellite. A strong pulse may be generated inside electronics. A genuine optical technosignature must survive these possibilities. Multiple detectors help. Multiple observatories help more. A pulse detected from the same celestial coordinates by stations separated across Earth would be difficult to explain as one local event. If the pulse repeated with the motion of a distant planet, confidence would rise. If it contained internal mathematical structure, the artificial explanation would become stronger. If radio telescopes detected a coordinated signal from the same source, the combined evidence might become extraordinary. This multi-wavelength approach may be essential. A civilization does not need to choose one channel. It could transmit a radio beacon and an optical pulse together. Radio might attract attention. The laser could carry more data, or the optical pulse might mark the moment when a radio message begins. Two independent forms of energy arriving from the same star with linked timing would be difficult for many natural processes to reproduce. Humanity might recognize the answer through coordination. A real signal could begin with one flash. Several seconds later, a narrow radio line appears, then another optical pulse. The intervals form a sequence. Observatories around the world confirm both. The source remains fixed beside one star. The radio frequency drifts with a known planet. The optical wavelength shifts in the same pattern. The two signals behave like parts of one system. This would be far stronger than an isolated mystery. The evidence would not depend upon one instrument or one type of radiation. It would reveal intention through agreement. No such confirmed pattern has been observed. Optical SETI searches have produced no verified extraterrestrial laser detection. Parna SETI, Laser SETI, Breakthrough Listen, and related programs continue expanding the amount of sky, time, and wavelength space examined. while current results remain consistent with no confirmed optical technosignature. This quiet result is scientifically useful. It shows that extremely bright, continuously directed lasers are not common among the particular nearby stars and observing periods already studied. It constrains some forms of detectable technology. It encourages researchers to examine weaker signals, shorter pulses, broader areas, and different wavelengths. The search becomes more complete through every absence. Yet the cosmic haystack remains immense. Imagine searching Earth's oceans for one glowing grain of sand. The grain appears only once each year. It shines for 1/1000th of a second. Its color is unknown. Its position changes, and the observer has examined only a few cups of water. A lack of detection would reveal very little about whether the grain exists. This comparison is imperfect, but it captures the scale. SETI does not examine one simple yes or no universe. It examines a multi-dimensional space of frequency, direction, time, intensity, repetition, polarization, modulation, and technology. Optical searches add more dimensions: pulse duration, wavelength, beam width, sky coverage, atmospheric conditions. A signal may exist while lying outside every region examined so far. This is why scientists avoid saying that silence proves solitude. The searches are meaningful, but incomplete. A civilization may also choose not to transmit bright beacons. Lasers directed across interstellar distances require energy and accurate pointing. A society may communicate only within its own system. It might use methods humanity cannot yet detect. Its transmissions could be encrypted or compressed. It may avoid broadcasting for cultural reasons. Or it may simply have no reason to direct a beam toward a small planet whose technological activity became visible only recently. Earth has produced detectable technology for a tiny fraction of its history. For billions of years, the planet contained life without radio or lasers. A distant observer could study Earth during almost any earlier era and find no obvious technological signal. The same may be true elsewhere. Intelligence may exist without creating beacons. Technology may appear only briefly. The period during which two civilizations use compatible communication systems may be narrow. One society sends optical pulses for 10,000 years. Another develops optical astronomy 1 million years later. Their histories never overlap. The galaxy can contain many technological civilizations across time while remaining quiet at any one moment. Light preserves the past, but only while it travels. A laser pulse crossing Earth before telescopes existed is gone. It does not remain waiting in space. A message could have passed through the solar system while dinosaurs lived. No detector recorded it. Another could arrive tomorrow. The difference between cosmic silence and contact may depend upon timing measured against billions of years. Continuous beacons would reduce this problem. A transmitter operating for millions of years would be more likely to overlap with younger civilizations. An automated beacon might be built for this purpose. It could monitor nearby systems and transmit whenever it detects technological activity. Earth's oxygen-rich atmosphere has been visible for a very long time, but its radio leakage is recent. A distant observatory may know that this planet contains life while remaining unaware of intelligence. Once it detects radar or atmospheric industrial compounds, it might activate a laser. The answer would begin only after Earth became recognizable as technological. The return time would still depend upon distance. A system 100 light-years away could be seeing Earth as it was in 1926. It might just now receive some of the earliest powerful radio evidence. If it responded immediately, the reply would not reach Earth until the 22nd century. A system 1,000 light-years away still sees Earth before modern science. Most of the galaxy has not yet had time to learn that humans exist. This makes the phrase already answered deeply dependent upon location. A nearby civilization could have received human signals and responded. A distant civilization could not. A laser may already be traveling toward Earth while remaining decades away. Nothing in present silence distinguishes between no sender and a message still in transit. The same uncertainty applies to signals already received. An optical pulse may have entered a telescope and been classified as an ordinary transient. Astronomical surveys record enormous numbers of changing objects. Supernovae brighten, variable stars pulse, asteroids move, satellites flash, detectors experience artifacts. Most events are processed automatically. A laser signal could be overlooked if it failed to match the assumptions of the search. Archives therefore matter again. Old images can be examined for brief point-like flashes. Spectra can be searched for narrow lines using new algorithms. Events detected by one survey can be compared with data from another observatory. A candidate dismissed years ago may become interesting after similar signals appear from the same location. Artificial intelligence may help uncover patterns too complex for simple filters. But algorithms carry their own assumptions. A system trained only on known natural events may reject something genuinely new. A system searching too broadly may produce millions of false candidates. Researchers must balance openness with practicality. The goal is not to label every anomaly as contact. It is to preserve enough unusual events for future comparison. A strong archive should allow the sky to be asked new questions later. This is one reason modern projects increasingly emphasize open data and coordinated observing. One telescope may record the pulse, another may unknowingly observe the same star, a third may hold a spectrum from the same minute. When these records are combined, an isolated flash can become a multi-instrument event. The answer may emerge through connection. Optical SETI also changes how another civilization might see humanity. Earth's most obvious optical technosignatures are probably not intentional interstellar lasers. City lights are faint compared with reflected sunlight. Most terrestrial lasers are narrow and aimed towards satellites, aircraft, the moon, or locations near Earth. Only observers positioned inside the beam would detect them. Powerful laser communication systems may become more common as humanity expands through the solar system. Beams between Earth, the Moon, Mars, and spacecraft could occasionally sweep past distant stars. An external observer might notice these communications. Our ordinary infrastructure could become someone else's candidate. This symmetry is useful. Scientists can ask how far away present or future Earth technologies would be detectable. The answer depends strongly on direction and instrument capability. High-powered, deliberately directed optical lasers could be visible across interstellar distances to suitable receivers, while everyday emissions would be much harder to recognize. By imagining Earth as the alien planet, researchers can design more realistic searches. Would an observer see one brief pulse? Would it repeat? How accurately must the telescope point? How many photons would arrive? Would atmospheric turbulence blur it? Could the signal be distinguished from the sun? These calculations turn speculation into measurable limits. They also reveal that detectability is not the same as existence. Earth contains technology. Most distant observers would not currently detect it. A search can fail even when the target is inhabited and technological. This is perhaps the most important lesson of optical SETI. Silence can arise from geometry. A laser is narrow. The sender points elsewhere. The receiver looks away. A cloud passes. The pulse arrives between exposures. The civilization transmits at another wavelength. The message remains invisible, without requiring anyone to be absent. But geometry can also create one perfect meeting. A beam leaves a distant planet. It widens slowly across the darkness. Years pass. The wavefront reaches the solar system. Earth rotates beneath a clear night sky. Two observatories are watching the same region. Their detectors register a cluster of photons within the same billionth of a second. The light is concentrated at one precise wavelength. No satellite crosses the field. No meteor appears. The signal repeats. Then it begins to count. Such an event has not occurred in the confirmed scientific record, but modern instruments are being built to recognize it more clearly than any previous generation could. For now, the optical sky has offered no verified answer from another intelligence. It has offered stars, flares, meteors, satellites, instrumental flashes, and vast numbers of natural transients. It has taught astronomers how difficult it is to watch everything. It has also shown that a message may be hidden not in a mysterious object, but in the exact timing and color of light. Radio searches listen for a voice across many frequencies. Optical searches watch for a blink. The blink may last less than a heartbeat. It may cross the galaxy unseen, or it may arrive when Earth is finally watching. Yet communication is only one way another civilization could answer. A world may reveal technology without transmitting anything toward us. Its atmosphere could contain chemicals created by industry. Its night side might glow. Its surface could reflect artificial materials. Its star's light might be altered by structures placed in orbit. The next part of the search therefore moves away from messages. It turns toward distant planets themselves. Perhaps the answer is not being sent. Perhaps it is already written in the light of another world. A distant civilization may never send a message toward Earth. Its planet may answer for it. Light leaving another world passes through its atmosphere, reflects from its surface, and carries traces of everything it encounters. Molecules absorb certain colors, clouds scatter others, oceans create glints, continents alter brightness as the planet rotates. If technology exists there, it may also leave a mark. The atmosphere could contain manufactured chemicals. The night side might glow with artificial illumination. Large fields of energy collectors could change the color of the surface. Orbiting machines might block tiny portions of starlight. And every machine using energy would eventually release some of that energy as heat. These possibilities belong to the search for planetary technosignatures. They do not require another civilization to know that Earth exists. They do not require a transmitter to remain pointed toward us. The planet simply continues moving around its star, while its light carries information outward in every direction. An answer written into a planetary atmosphere might cross space continuously for centuries. Humanity would only need to learn how to read it. Astronomers already study some exoplanet atmospheres by observing planets as they pass in front of their stars. During a transit, a small fraction of the star's light travels through the outer layers of the planet's atmosphere before reaching the telescope. Molecules within that atmosphere absorb particular wavelengths. The resulting spectrum acts like a distant chemical barcode. Water vapor absorbs one collection of wavelengths. Carbon dioxide absorbs another. Methane, oxygen, ozone, and many other molecules each leave characteristic features. The measurement is extraordinarily delicate. The planet may block only a small fraction of the star. Its atmosphere blocks an even smaller fraction. Astronomers must separate the planet's faint chemical imprint from the much brighter star, the telescope's instruments, and sometimes Earth's own atmosphere. Yet this method has already revealed molecules in the atmospheres of many large exoplanets. The long-term goal is to extend atmospheric characterization towards smaller, temperate, rocky worlds. There, researchers can search for biosignatures associated with life and technosignatures associated with technology. A biosignature and a technosignature are related, but they do not answer exactly the same question. A biosignature may suggest that biology has changed a planet. A technosignature suggests that technology has changed it. Oxygen combined with methane might indicate a living biosphere under suitable conditions, though every proposed biosignature must be interpreted within the full planetary environment. A manufactured industrial compound could point more directly toward technological activity if natural processes cannot produce it in meaningful quantities. The challenge is finding chemicals that satisfy several conditions. They must be strongly detectable. They must remain in the atmosphere long enough to accumulate. They must not be produced easily by geology, stellar radiation, or ordinary atmospheric chemistry, and the civilization must release enough of them to affect the planet's spectrum. On Earth, industrial activity has produced substances that were rare or absent in the natural atmosphere. Chlorofluorocarbons, often called CFCs, were manufactured for uses such as refrigeration and aerosol products. Some damage the ozone layer and also act as powerful greenhouse gases. Nitrogen dioxide is produced naturally by processes including lightning and biological activity, but large concentrations can also result from combustion and industry. Researchers have explored whether gases like these might become detectable in the atmosphere of an inhabited exoplanet. The idea is sometimes described as searching for alien pollution, but the word pollution reflects a human judgment. From a distant telescope, the molecule would simply be evidence that a process is operating. Whether it is an unwanted byproduct, a deliberate atmospheric modification, or part of a technology unlike anything on Earth would remain unknown. An extraterrestrial civilization may not repeat Earth's industrial history. It may develop cleaner energy systems. It may avoid compounds that remain in the atmosphere. It could live beneath an ocean, below the surface, or inside structures that recycle nearly every material. Its industries may produce molecules humanity has never manufactured. Searching only for familiar pollutants, therefore, carries a quiet limitation. It assumes that another technological world leaves traces resembling ours. But Earth provides the only known example of a technological planet. Researchers begin with it because there is nowhere else to begin. The atmosphere above modern Earth contains a record of agriculture, combustion, refrigeration, transportation, energy production, and chemistry. An astronomer on a nearby world would not see factories directly. It might infer them from the combined effect of many activities. This thought experiment allows scientists to ask a practical question. How far away could present-day Earth be recognized as technological? The answer depends upon the technosignature. Some of Earth's radar emissions could be detectable across far greater distances than its atmospheric pollutants or artificial lights. Planetary atmospheric effects are more subtle and would generally require closer systems, more advanced instruments, or a civilization producing stronger signatures than modern humanity. A distant planet may be technological and still appear completely natural to current telescopes. Existence does not guarantee detectability. There is also no rule that an artificial atmospheric gas must be accidental. Technology could alter a planet's climate deliberately. A civilization living on a cooling world might release long-lived greenhouse compounds to preserve liquid water. It might warm a neighboring frozen planet before settlement. It could modify the atmosphere of a moon or maintain a stable temperature beneath a dimming star. Some proposed artificial greenhouse gases absorb strongly in the middle infrared portion of the spectrum and have few expected natural sources. A 2024 study examined compounds including sulfur hexafluoride and several fluorinated carbon gases as possible signs of intentional planetary warming. The researchers modeled whether concentrated amounts could be found in observations of a world such as TRAPPIST-1F. Their calculations suggested that sufficiently high atmospheric concentrations could, under favorable circumstances, leave features accessible to repeated observations with instruments like those aboard the James Webb Space Telescope. This remains a theoretical detectability study. No such gases have been detected on TRAPPIST-1F or any other exoplanet. The work demonstrates what an artificial atmosphere might look like, not that one has been found. The distinction is important. Scientists often model possible technosignatures years before telescopes become sensitive enough to search for them effectively. They calculate what a signal would do to light. They test whether natural chemistry could imitate it. They estimate how many observations would be required. This preparation turns an unfamiliar future spectrum into something recognizable. Without such models, an artificial molecule might be observed and misidentified as noise or an unknown natural process. Theoretical studies create a library of possibilities. The library does not prove that any of those possibilities exist. It prepares the instruments to notice them if they do. A convincing atmospheric technosignature would probably involve more than one molecule. One compound may have an unexpected natural source. Several manufactured compounds appearing together would be harder to explain. The atmosphere might contain a family of gases whose abundances do not fit known photochemistry. Their concentrations could rise and fall with a planetary season. They might cluster above one region. They could exist alongside biological gases and a temperate climate. The complete planetary context would matter. Astronomers would need to know the star's ultraviolet radiation, the planet's temperature, pressure, surface conditions, and atmospheric circulation. A molecule cannot be interpreted separately from the world containing it. Even oxygen, often discussed as a biosignature, can arise without life under certain planetary conditions. Technology requires the same caution. A substance unusual on Earth may form naturally under a different star or within an atmosphere unlike ours. A confident claim would require models showing that the observed combination is extremely difficult to produce without manufacturing. Independent instruments would need to recover the same spectrum. The spectral features would need to appear repeatedly as the planet moved through its orbit. A planetary answer would emerge slowly, not as one dramatic pulse, as many nights of light gathered and compared. The signal might be spread across only a few missing colors. Artificial illumination offers another possibility. A planet reflects its star during the day. Its night side should normally become much darker. Natural glows may remain. Auroras can illuminate polar regions. Lightning can flash within clouds. Volcanic activity can produce light. Air glow can arise when atmospheric atoms and molecules release stored energy. Bioluminescent organisms may brighten portions of an ocean, but a technological civilization could produce organized illumination across cities, roads, habitats, industrial areas, or orbital stations. From interstellar distance, individual lights would merge into one faint glow. No telescope would see streets. It would see a small amount of brightness where darkness was expected. NASA includes artificial night-side illumination among the possible non-radio technosignatures that future observatories might investigate. Capturing the glow of city-like lighting on a rocky planet would be extremely difficult, but its organized presence could provide strong evidence of technology. The easiest artificial lights to detect might not resemble modern cities. Earth's night side is faint compared with its daylight side. Most human lighting is designed for people on the ground, not observers among the stars. Buildings and streets direct only part of their light upward. Clouds and the atmosphere scatter some of it. From far away, Earth's city lights would disappear beside the brightness of the sun and the illuminated crescent of the planet. A civilization intentionally creating a beacon could make itself much more visible. It might illuminate a large region with one narrow color. It could arrange light into repeating geometric patterns. It might brighten the night side during moments when the planet lies favorably separated from its star. Instead of ordinary urban lighting, it could construct a planetary display. Such a project would require extraordinary energy. But detectability studies do not ask whether another civilization would definitely choose it. They ask what a telescope could notice if it did. A planet's phases offer one way to separate artificial illumination from reflected starlight. Like the moon, an exoplanet shows changing phases as it travels around its star. During a fuller phase, the day side dominates. Near a crescent phase, more of the visible hemisphere belongs to the night side. A natural planet becomes dimmer as its illuminated portion narrows. Artificial night side light could change that pattern. The planet might remain slightly brighter than expected near crescent phases. Its spectrum could also contain narrow emission bands associated with artificial sources. Repeated measurements throughout the orbit would reveal whether the additional light returns with the same planetary longitude. As the planet rotates, bright regions might move into and out of view. A repeating map could gradually emerge from unresolved light. Astronomers already use changing brightness to study clouds, rotation and surface variation on solar system worlds and some exoplanets. Future telescopes may apply related methods to smaller rocky planets. The planet would remain a single point of light, yet the point would change. From those changes, researchers could infer oceans, continents, weather, and perhaps artificial illumination. The world would become a map without ever becoming a photograph. Imagine observing a distant planet every evening for several months. Its brightness rises and falls with its orbit. A smaller variation repeats every 26 hours. That shorter rhythm represents rotation. One region reflects blue light, another appears darker. Clouds change unpredictably, but one narrow amber emission returns at the same phase of every rotation. It remains visible when that region moves onto the night side. The signal grows during the planet's local evening and fades near its morning. No known aurora or atmospheric process explains the pattern. A second telescope confirms it. The repeating glow would not tell humanity who built it, but it could reveal that the night on another world is not entirely natural. Surface materials may leave more subtle signs. Human technology has covered parts of Earth with concrete, glass, metals, roads, roofs, and solar panels. These materials reflect light differently from forests, oceans, deserts, snow, and rock. A sufficiently widespread artificial surface could alter a planet's overall spectrum. Researchers have considered whether large arrays of silicon solar cells might produce recognizable reflectance features. Solar panels absorb some wavelengths efficiently and reflect others. If they covered a significant portion of a planet, the combined reflected light might carry an unusual pattern. A NASA-led study examined how detectable large-scale silicon solar panel coverage could become on an Earth-like exoplanet. The analysis suggested that a civilization with energy needs comparable to or moderately beyond modern humanity might require only a relatively small portion of its land for solar collection, making the global signature difficult to detect. A civilization does not automatically become easier to find as it becomes more advanced. Greater efficiency, compact energy systems, or technologies unlike silicon panels could make it quieter. This is a useful correction to an older assumption. Technological growth does not necessarily lead to enormous visible structures. Human devices often become smaller and more efficient. Communication moves from powerful broadcasting toward narrow beams, fiber optic cables, and low-power networks. Lighting becomes better directed. Pollution can decline as technology improves. Energy systems may produce fewer atmospheric byproducts. A mature civilization could become less visible than an early industrial one. Its technosignatures may peak during a temporary phase. For several centuries, a world releases pollutants, broadcasts powerful radio waves, and illuminates large cities. Later, it cleans the atmosphere, shifts communication into tightly directed channels, recycles materials, and uses compact energy sources. The civilization continues. Its astronomical brightness fades. Earth may presently occupy an unusually visible technological period, or perhaps it is only beginning to become visible. No one knows which direction long-term technological evolution usually takes. There may be no usual direction at all. Some societies could expand outward and construct visible infrastructure. Others may concentrate inward. Some might alter planets. Others may preserve them carefully. The search must remain broad enough to include both loud and quiet technology. Heat provides one of the broadest possibilities because no energy system is perfectly efficient. A machine can convert energy into motion, computation, communication, or stored chemical energy. But some energy eventually disperses as heat. A building warms the air. A computer warms its surroundings. On a planetary scale, industry and energy use may slightly raise the amount of thermal radiation escaping into space. For a civilization using vastly more energy than modern humanity, this waste heat could become detectable. The planet might appear warmer than expected from the starlight it receives. Its infrared spectrum might contain excess radiation that ordinary climate models cannot explain. NASA and SETI researchers include infrared waste heat among the central non-radio technosignatures, because energy use of almost any kind must eventually interact with thermodynamics. Waste heat does not necessarily indicate careless engineering. Even a nearly perfect machine must dispose of energy eventually if it continues operating. Computation transforms ordered energy and produces heat. Collected starlight becomes heat after use. A civilization may radiate that heat at temperatures chosen to make its systems efficient. The wavelength of the radiation depends upon temperature. Warm surfaces glow mainly in infrared light. Cooler radiators glow at longer infrared wavelengths. A civilization attempting to hide could spread its heat across large cold structures, making the signal more difficult to separate from natural dust. It could never make the energy disappear entirely. It could only change how and where it leaves. This makes waste heat appealing as a general search target. Radio assumptions depend upon communication habits. Industrial gases depend upon chemistry. City lights depend upon visual needs. Solar panels depend upon one form of energy collection. Waste heat arises from physics shared by every technology that uses energy. Yet natural objects also glow in infrared. Planets emit heat. Dust around stars absorbs visible light and re-radiates it in the infrared. Young stellar systems contain warm disks. Old stars shed material. Galaxies contain clouds where new stars are forming. A warm infrared excess is therefore not automatically artificial. The search asks whether the amount, temperature, and distribution of the heat fit known astrophysics. A planet receiving a certain amount of starlight has an expected range of temperatures. Its atmosphere can modify that range. Internal heat can contribute. Tidal forces can warm it. Volcanism can release energy. Only after these sources are understood could unexplained thermal emission become a plausible technosignature. Again, artificiality would appear through context. Suppose a rocky planet reflects the amount of starlight expected from its surface and atmosphere. Its orbit is known. Its greenhouse gases are measured. Yet the planet releases significantly more infrared energy than the star can provide. No strong tidal interaction exists. The interior is not young enough to explain the excess. The additional heat varies according to regions on the surface. Those regions also contain artificial atmospheric compounds or night-side light. Each observation alone might remain uncertain. Together, they would begin forming a technological picture. Multiple technosignatures from the same world would be much more persuasive than one anomaly. Industrial gases could indicate manufacturing. Night-side illumination could indicate organized settlement. Waste heat could reveal energy use. Narrow radio signals could reveal communication. An orbiting structure could produce unusual transits. The different signs would support one another. A planet would not merely look strange in one way. It would look consistently technological. This is how Earth might appear to an exceptionally capable distant observatory. One instrument notices radar. Another detects atmospheric nitrogen dioxide and manufactured compounds. A future telescope sees a faint night-side glow. Infrared measurements reveal heat concentrated around populated regions. Satellites create subtle, changing reflections. No single feature contains a message saying humanity lives here. The complete collection does. Earth answers through its systems. A distant civilization might do the same. The search for several signatures also helps reduce false positives. A natural process may imitate one signal. It is less likely to imitate many independent signals in a coordinated way. A volcano can release unusual gases and heat. It does not usually produce narrow radio transmissions organized around prime numbers. Auroras can create night-side light. They do not usually manufacture stable fluorinated compounds. Dust can cause infrared excess. It does not normally illuminate the night side of one orbiting rocky planet in repeating geometric regions. A technological interpretation becomes stronger when different forms of evidence converge. Astronomers sometimes use the phrase multiple lines of evidence. The lines may come from different telescopes, wavelengths, and scientific disciplines. Atmospheric chemists study molecules. Planetary scientists model climate. Radio astronomers examine signals. Infrared astronomers study heat. Engineers estimate what technology could produce. The discovery of another civilization may not belong to one field. It could emerge from the place where many fields overlap. Future observatories are being designed mainly to answer broader questions about exoplanets, including whether nearby rocky worlds possess atmospheres and signs of life. The proposed Habitable Worlds Observatory is intended to directly image potentially habitable planets around nearby stars and analyze their light. Technosignatures such as industrial pollutants, artificial illumination, or large structures may become additional targets within the same observations. A telescope does not need to be built only for SETI to contribute to it. Data gathered for climate and biosignature studies can also be searched for technology. Direct imaging would represent an important change. Transit spectroscopy works best when a planet's orbit happens to carry it across its star from Earth's perspective. Most planetary systems are not aligned this way. Direct imaging attempts to separate the planet's own light from the star beside it. This is difficult because a star can be billions of times brighter than a small reflected light planet. Coronagraphs and star shades are designed to block or redirect starlight while preserving the faint point nearby. Once the planet is isolated, its spectrum and changing brightness can be studied throughout its orbit. Researchers could examine worlds that never transit. They could search for atmospheric gases, oceans, clouds, seasonal changes, surface materials, and possible technosignatures. The star's glare remains the central obstacle. It is like trying to see a small reflective object beside a lighthouse from thousands of kilometers away. The telescope must remove the lighthouse's light with extraordinary precision. Any imperfection can imitate or hide the planet. Wavefront control, stable optics, sensitive detectors, and careful calibration become essential. This challenge explains why the clearest images of Earth-like exoplanets do not yet exist. Humanity knows of thousands of worlds, but most appear only through indirect measurements. Their gravity moves their stars. Their transits reduce starlight. Their heat or reflected light appears as a faint signal. A technological planet may already exist within these catalogs while remaining unresolved. Its name could be a string of letters and numbers. Its radius may be known. Its year may be measured. Yet its atmosphere and surface remain hidden. The answer could already have a catalog entry without having a recognizable identity. This possibility gives another meaning to the phrase already answered. The information may have reached Earth. Astronomers may have detected the planet, but the signal has not yet been interpreted at the level required to reveal technology. The answer is present only in an incomplete form. A future telescope returns to the same world and separates its light. Manufactured gases appear. The planet's night side glows. An old data point becomes the beginning of a discovery. Many major astronomical objects were observed before their true nature was understood. Ancient observers saw planets as wandering lights long before they knew they were worlds. Nebulae appeared as faint clouds before telescopes resolved stars and galaxies within them. Unusual stellar motions were measured before unseen planets were identified. Detection often comes before recognition. A technological exoplanet could follow the same path. The first evidence may already sit inside measurements collected for another purpose. But caution must remain. Every unusual spectrum contains many possible sources of error. Stellar activity can contaminate atmospheric measurements. Sunspots and bright regions on a star may change the light passing through a planet's atmosphere. Instrumental effects can create false absorption features. Clouds can hide molecules. Different gases may produce overlapping bands. A planet's mass and temperature may remain uncertain. A claimed technosignature would require repeated observations and independent analysis. The history of exoplanet atmospheres already includes debated molecular detections. Some signals become weaker when new data arrive. Others depend upon how the instrument is calibrated or how the atmosphere is modeled. Technology would not be exempt from these difficulties. A molecule described as artificial could later be produced in a laboratory by a natural reaction. A night-side glow could be an aurora. An infrared excess could be dust. A surface spectrum could come from an unfamiliar mineral. The strongest claim would be the one that remains after every ordinary possibility is investigated carefully. This process may take years. The first paper reports an unusual gas. Other researchers analyze the same data. New observations test the feature. Laboratories study whether the molecule can form naturally. Climate models determine whether it can survive. A second instrument measures another wavelength. Perhaps a radio telescope begins monitoring the system. The answer becomes clearer through patience. There is no need for one announcement to contain everything. Scientific discovery often develops through stages. A candidate, a confirmation, a physical interpretation, a broader context, only then a conclusion. A planetary technosignature may also disappear while being studied. Civilizations change. An atmospheric compound may decline after environmental regulation. City lights may dim as energy systems improve. A global project could operate for only a few decades. From Earth, those changes would be observed in the distant past. A planet 100 light-years away might reveal an industrial era that ended there a century before the light arrived. Technology becomes visible as history. Long-lived compounds could preserve that history. Some artificial gases remain in an atmosphere for centuries or longer. They may outlast the factories that produced them. Structures may survive after abandonment. Waste heat fades when machines stop. City lights vanish quickly. Each technosignature has its own lifetime. Radio pulses may last seconds. Atmospheric chemicals may last centuries. Orbital artifacts could persist for millions of years under stable conditions. The galaxy may therefore contain overlapping layers of technological time. Signals from living civilizations. Pollution from recently changed ones. Artifacts from vanished ones. A telescope may detect not a present society, but the residue of one. The answer could be archaeological. This possibility becomes even stronger when the search expands beyond individual planets. A civilization using large amounts of stellar energy might construct structures around its star. Swarms of collectors could intercept light and re-radiate energy as infrared heat. Large objects could produce unusual dips as they crossed the star. Engineered patterns might appear within a light curve. These ideas are often associated with Dyson spheres and other stellar-scale projects. They represent a form of technology much more visible than city lights or atmospheric pollution. They also carry much greater uncertainty. Natural dust, comets, planets, and stellar activity can create many similar effects. The next part of the journey turns toward these enormous possibilities. Toward stars that dim in unexpected ways. Toward infrared glows that seem too warm. Toward the idea that an answer may not be written on one planet at all. It may surround an entire sun. A message may be brief. A structure can remain visible for thousands of years. This is why some searches for extraterrestrial intelligence look not for signals, but for architecture. A civilization capable of using only the energy falling upon one planet might remain difficult to detect. Its radio transmissions could be narrow. Its cities could be faint. Its atmospheric changes might be subtle. But a civilization requiring far greater energy could begin building outward. It might place collectors close to its star. More collectors could follow. Over centuries, the number might grow from thousands to millions. They could orbit at different distances, absorbing part of the star's light and providing energy to habitats, computers, factories, spacecraft, or communication systems. From Earth, these machines would remain far too small to photograph individually. Their combined effect might still be visible. Some starlight would disappear. The system would glow unusually in infrared radiation, and the star might dim in patterns that planets, dust, and ordinary stellar activity struggle to reproduce. The broad idea was described scientifically by physicist Freeman Dyson in 19. Dyson suggested that a technologically developed society with increasing energy requirements might eventually capture a substantial fraction of its star's radiation. He proposed that astronomers search for stellar sources whose visible light had been transformed into infrared emission. The concept later became known as a Dyson sphere. The name often creates an image of one solid shell completely enclosing a star. A more flexible version involves a vast swarm of independent objects. Some may collect energy, others may contain habitats. Some could reflect light or transmit power. Each object would orbit separately, like an artificial cloud surrounding the star. The swarm could begin small. It would not need to appear all at once. A civilization might gradually add structures as its population, industry, or computing requirements increased. At first, the system would block only a tiny fraction of its star. Later, the coverage could become substantial. The star might appear slightly dimmer in visible light and unusually bright in the infrared. This infrared glow comes from a basic physical principle. Energy does not vanish after being used. A collector absorbs high-temperature starlight. Part of that energy may become electricity, movement, communication, or computation. Eventually, much of it becomes heat. The structures must release that heat into space. At temperatures comfortable for machinery or biological habitats, the radiation would emerge mainly at infrared wavelengths. The star's visible energy would be reorganized. Instead of one hot point shining brightly in visible light, an observer might see a cooler, larger region glowing in the infrared. This is sometimes called waste heat. The name does not mean the civilization is inefficient. Even highly efficient technology must release energy after useful work is performed. The temperature and wavelength of that release could vary greatly. Structures close to a star might be hot. Collectors farther away might radiate more gently. A civilization could construct large cool radiators to shift the glow toward longer wavelengths. But unless it stores energy forever or sends it away in a narrow beam, some thermal signature should remain. This makes infrared astronomy useful for technosignature searches. Astronomers do not need to understand the civilization's language. They do not need to know what its machines are doing. They search for an imbalance. Too little visible starlight. Too much infrared heat. A star that seems to be wrapped in something. Yet nature already creates this pattern in many ways. Young stars form inside clouds of gas and dust. Disks of material orbit them while planets are being assembled. Dust absorbs the star's visible and ultraviolet light, warms and radiates in the infrared. Older planetary systems can also contain debris disks. Asteroid collisions produce fine particles. Comets release material. Stars eject gas late in their lives. Distant galaxies filled with dust can appear near a foreground star by coincidence. All of these can create infrared excess. A strange infrared source is therefore not automatically an artificial structure. It begins as a candidate requiring a careful study of its age, motion, spectrum, environment, and position. NASA's technosignature research describes excess infrared radiation as a possible sign of large energy-collecting structures, while emphasizing that young dusty stars provide a common natural explanation. The search resembles looking across a nighttime city for one unusual lamp while standing inside a field of warm fires. Many natural objects glow in infrared. Technology must be separated from the background. The most persuasive system would probably combine several properties. It would be an ordinary mature star rather than a young object still surrounded by planet-forming material. It would show no signs of a familiar debris disk. A substantial portion of its visible light would appear missing. The missing energy would reappear as thermal radiation. The temperature of that radiation might resemble the operating environment of artificial structures rather than the broad temperatures found in natural dust. The system could also vary in organized ways. Perhaps individual collectors would cross the star. The resulting dips might have unusual shapes. A planet creates a smooth, rounded reduction in light as its circular silhouette moves across the stellar surface. An artificial object could possess sharp edges. A triangle, rectangle, or formation of separate panels might produce a more complicated light curve. The exact shape would depend upon orientation, speed, size, and the brightness pattern across the star. One unusual transit would not be enough. Comets can create asymmetrical dips. Dust clouds can change shape. Multiple planets can overlap, Fragments from collisions can produce irregular patterns, but repeated transits following stable geometric rules could become interesting. A large structure might return at the same orbital period. Its light curve could retain corners, steps, or repeated substructures. Several objects might cross in coordinated formations. The dimming could increase over time as the swarm grew. Astronomers would then search for the accompanying infrared heat. The blocked starlight and the thermal emission should fit together. If 10% of a star's energy disappeared from visible observation, a corresponding amount should emerge somewhere else, unless it was redirected away. Energy accounting becomes part of the evidence. The star cannot simply become dimmer without explanation. Its energy must move into another form. A structure can hide the light, it cannot erase physics. This idea became widely discussed when one particular star began dimming in a way that seemed unlike an ordinary planet. The star is officially known as KIC 8462852. It is also called Boyajian's star or Tabby's star. NASA's Kepler Space Telescope observed it while monitoring the brightness of more than 100,000 stars. Kepler's main purpose was to find planets through transits. A planet crossing a star generally creates a small, regular dip. Jupiter passing in front of a sun-like star blocks about 1% of the light. Earth blocks far less. Tabby's star produced dips reaching roughly 20%. The events were irregular. They differed in depth and duration. They did not follow the clean rhythm expected from one orbiting planet. Something appeared to be obscuring a remarkable portion of the star, then changing before the next event. The data had first attracted attention through the Planet Hunters citizen science project. Volunteers examined stellar light curves and noticed behavior that automated planet searches had not classified normally. The star became an example of how human pattern recognition can find anomalies inside enormous datasets. Many explanations were considered. A family of comets could create irregular clouds. Fragments from a planetary collision might pass across the star. Dust could be distributed unevenly around the system. The star itself might undergo unfamiliar changes. And as a more speculative possibility, large artificial structures could block portions of the stellar surface. The artificial interpretation captured public imagination because the dips seemed so deep. A swarm of collectors could, in principle, produce irregular reductions in visible light. If different structures crossed at different times, the light curve might appear complicated. But an interesting shape is not positive evidence of engineering. The star had to be studied across many wavelengths. Dust and solid structures interact with light differently. A large opaque object blocks visible, ultraviolet, and infrared wavelengths more evenly. Small dust grains scatter shorter wavelengths more strongly. The star should therefore appear redder during dust-related dimming, because more blue and ultraviolet light is removed. Observations using NASA's Swift and Spitzer missions, together with ground-based measurements, found that the long-term dimming was stronger at shorter wavelengths and weaker in the infrared. That wavelength dependence points towards small particles rather than large opaque megastructures. An uneven cloud of dust became the leading explanation for the long-term behavior. This did not make every detail of Tabby's star immediately simple. The source and arrangement of the dust continued to invite study. Different dimming events may involve material with changing particle sizes and distributions. The system remains scientifically unusual, but the observation that the dimming depends upon wavelength is an important piece of evidence against the simplest megastructure explanation. A vast opaque panel should not selectively remove ultraviolet light more strongly than infrared light. Fine dust does exactly that. The mystery moved from imagined architecture toward planetary debris and circumstellar material. This is a common path in technosignature research. A candidate first appears because it does not fit an expected natural pattern. Astronomers then gather new kinds of data. The candidate becomes more interesting only if natural explanations become weaker. Tabby's star moved in the opposite direction. The additional wavelengths gave dust a stronger role. No confirmed artificial structure was found, yet the star changed the search. Before it, artificial transits were often discussed mainly through theoretical models. After it, astronomers had a real example of a star whose brightness could imitate parts of that expectation. Researchers learned how strongly irregular dust can resemble engineering when only one wavelength or one period of observation is available. They also learned the value of public monitoring. When Tabby's star began dimming again, telescopes around the world could observe it quickly. Amateur astronomers helped track its brightness. Professional observatories measured its colors and spectrum. A mysterious event became a coordinated experiment. The star acted almost like a practice signal. It showed how a future candidate might be examined. First, confirm the dimming independently. Then observe at many wavelengths. Search for infrared heat. Measure polarization. Study the star's age and activity. Look for gas, dust, companions, and planetary material. Check whether the event repeats. A real structure must remain convincing after all of these measurements. The search for Dyson-like systems is not limited to stars already known to dim strangely. Large sky surveys can compare millions of objects at once. The Gaia mission measures positions, distances, and motions for stars throughout the Milky Way. The 2-micron all-sky survey recorded near-infrared light. NASA's WISE mission mapped the sky at mid-infrared wavelengths. By combining these catalogs, researchers can ask whether a star appears normal in visible and near-infrared light, but possesses an unexpected glow at longer wavelengths. The process begins with an enormous population. Most objects are removed quickly. Young stars are excluded because dust is common around them. Variable stars may be removed. Known galaxies, nebulae, and crowded regions are treated carefully. Researchers compare the measured light with models of ordinary stars and hypothetical partial Dyson structures. Every filter reduces the list. Millions become thousands. Thousands become dozens. Perhaps only a few remain for detailed follow-up. In 2024, Project Hephaestus reported such a search using Gaia, 2MASS, and WISE data. The study began with approximately 5 million objects and identified 7 M-dwarf stars whose infrared excesses were considered worthy of further investigation. The authors did not claim that these stars contained artificial structures. They presented them as candidates that survived the project's initial filters and required better observations. M-dwarfs are small, cool stars. They are the most common stellar type in the Milky Way. Their lower visible brightness can make additional infrared emission easier to notice. But they also create interpretive difficulties. Dusty objects, stellar activity, unresolved companions, and sources positioned behind them can affect the measurements. WISE was designed to survey the entire sky rather than produce extremely sharp images of every crowded field. Its longer wavelength images can blend objects separated by only a small angle. A nearby red dwarf may appear as one point in optical data. A distant infrared bright galaxy may sit almost directly behind it. WISE may combine their light into one source. The catalog then appears to describe a star with excess infrared radiation. In reality, the visible light belongs mainly to the star, while the infrared glow belongs mainly to a galaxy far beyond it. From Earth, the two objects align like distant lanterns viewed along the same narrow path. This problem is called source confusion. It is especially important when catalogs from telescopes with different resolutions are combined. A sharp optical image can separate objects that a broader infrared image merges together. The resulting spectral energy distribution may look like one exotic object even though it is created by two ordinary ones. Project Hephaestus therefore became not an announcement, but the beginning of a follow-up story. Astronomers searched for radio emission near the candidates. They examined the precise positions of the optical and infrared light. They studied deeper images. They asked whether the center of the source appeared to shift at different wavelengths. A shift would suggest that the visible star and the infrared source were not located at exactly the same position. Several candidates began showing signs of nearby background contamination. The strongest test came from the James Webb Space Telescope. JWST's mid-infrared instrument can observe with much finer detail than the older all-sky WISE images. Two Project Hephaestus candidates, called D and E in the study, were observed with JWST in 2025. The results were reported in July 2026. The sharper images separated each M-dwarf from a very close infrared bright background galaxy. For both systems, the excess heat did not arise from structures surrounding the nearby star. It came from distant dusty galaxies, projected almost along the same line of sight. Spectroscopy identified one as a hot, dust-obscured galaxy, and the other as a dusty star-forming galaxy. The candidate had not been imaginary. The infrared light was real. The mistake lay in assigning that light to the foreground star. WISE saw two sources as one. JWST separated them. This is one of the most instructive outcomes possible. The search pipeline had successfully found unusual combinations of visible and infrared measurements. The follow-up then revealed a previously unresolved astronomical alignment. No alien technology was required, but the investigation improved future searches by showing exactly how a strong false positive can arise. Recent archival analyses have also found evidence of background objects or positional inconsistencies near several other Project Hephaestus candidates. Some targets still require dedicated observations, but none has become a confirmed Dyson structure. The JWST results show that very close, infrared bright galaxies may contaminate more candidates than simple catalog estimates initially suggest. This does not make large-scale searches ineffective. It shows why candidates and discoveries are different stages. A sky survey is designed to find unusual sources efficiently. It cannot provide complete knowledge of every target. Its purpose is to create a manageable list. Sharper telescopes then examine that list. Most candidates are expected to become natural objects. A good search does not avoid every false positive. It identifies false positives in ways that teach the next search how to improve. Future pipelines can compare the exact centers of optical and infrared emission earlier. They can use deeper images to identify faint background galaxies. Machine learning systems can be trained on known cases of source confusion. Radio observations may reveal active galaxies behind foreground stars. High-resolution infrared instruments can test the strongest remaining candidates. Each ordinary explanation becomes a new filter. The search gradually learns the shapes of everything that is not a Dyson structure. This is similar to radio SETI. Human interference dominates the candidates. In infrared SETI, dust and galaxies dominate. Different instruments hear different backgrounds. The challenge is not merely detecting something unusual. It is understanding the universe well enough to know when the unusual cannot be natural. The search can also move beyond single stars. A civilization that expanded across a large portion of a galaxy might use enough energy to alter the galaxy's combined infrared appearance. Billions of stars would contribute. If significant fractions of their light were absorbed and re-radiated as heat, the galaxy could look dimmer in visible wavelengths and unusually bright in the mid-infrared. This would be a far larger technosignature. Individual structures would remain invisible. Their combined thermodynamic effect might become measurable across millions of light years. Infrared galaxy surveys have searched for systems with extraordinary waste heat fractions. Natural galaxies again create a rich background. Dusty star formation produces large amounts of infrared light. Active galactic nuclei heat surrounding material. Colliding galaxies can become infrared bright. A candidate must be distinguished from these known sources. Surveys using WISE have placed limits on how common galaxies dominated by warm artificial waste heat could be. They have not found a confirmed galaxy-spanning technological civilization. Research has generally found that galaxies converting very large fractions of their starlight into moderate temperature waste heat are uncommon in the nearby universe. This result must be interpreted narrowly. It does not show that galaxies contain no civilizations. It shows that certain extremely energy-intensive, infrared bright civilizations are not common within the regions and temperature ranges examined. A galaxy could contain many technological societies without any of them constructing vast stellar collectors. Even a civilization using a star's full output might radiate heat at temperatures outside a survey's most sensitive range. It could direct substantial energy into beams. It might build around only a small number of stars. Its structures could be cool enough to blend with natural dust, or it may use efficient technology whose astronomical effects remain subtle. Null results constrain possibilities. They do not close the entire question. This distinction matters because Dyson structures are sometimes treated as the inevitable future of intelligence. They are not. They are one hypothetical response to increasing energy demand. Another civilization may choose stability rather than continuous growth. Its population might remain limited. Its computers could become more efficient. It might move operations to colder locations where computation requires less energy. It may value unaltered stars and planets. Its technology could pursue goals unrelated to expansion. Humanity cannot assume that every intelligence eventually surrounds its star. The Dyson idea remains valuable not because it predicts what all civilizations must do, but because it describes something telescopes can search for. A useful technosignature does not need to be inevitable. It needs to be physically possible and observationally recognizable. Radio transmitters are not inevitable. Lasers are not inevitable. Industrial gases are not inevitable. City lights are not inevitable. Stellar collectors are not inevitable. Each method examines one possible way technology interacts with the universe. Together, they reduce dependence upon any one assumption. A civilization that never communicates may still release heat. One that produces little heat may use lasers. One that uses no visible lasers may alter its atmosphere. One that leaves its atmosphere unchanged may construct probes. The search remains broad because technology may express itself in many forms. Large stellar structures have one special advantage. They could outlive their creators. An individual radio message passes. An atmospheric pollutant eventually breaks apart. A swarm of orbiting collectors might remain for much longer. If its control systems failed, the swarm could slowly change. Objects might collide. Some orbits could remain stable. Fragments might create unusual dust. The system could become a technological ruin. From Earth, the distinction between an active civilization and an ancient artifact might be impossible at first. The infrared glow would show that energy was being absorbed and released. It would not reveal who maintained the structures. A repeating transit might show machinery still in orbit. It would not reveal whether the builders still lived. The answer could come from a civilization that ended before humanity began. Light would carry its architecture forward. An artificial system 1,000 light-years away is observed as it existed 1,000 years ago. A structure 10,000 light-years away is seen in a much earlier era. The Milky Way becomes not only a map of distance, but a collection of different times. A distant swarm could be active in the light reaching Earth, while having already changed at its true location. Communication would remain uncertain, but evidence of its existence could survive. This makes stellar engineering partly an archaeological search. Astronomers look for the cosmic equivalent of walls, roads, and abandoned cities. Only the scale is different. The wall may orbit a sun. The road may be a sequence of power stations. The ruin may glow in infrared across interstellar distance. No such artifact has been confirmed. Tabby's star is best explained through dust rather than opaque structures. The strongest modern infrared candidates are being reduced through higher resolution imaging and recognition of background galaxies. Large surveys have not identified a nearby star or galaxy whose energy distribution requires extraterrestrial engineering. As of 2026, the scientific record contains no verified Dyson sphere or Dyson swarm. Yet the search has become far more capable. Gaia supplies precise distances and motions. WISE provides an all-sky infrared map. JWST can separate close sources and obtain detailed spectra. Machine learning can compare millions of stars. Radio and optical telescopes can examine the same candidates for independent signs of technology. A suspicious infrared star can now be tested in several ways. Does its position shift with wavelength? Is a background galaxy visible? Does the heat resemble natural dust? Does the star show signs of youth? Are narrow radio signals present? Do optical lasers appear? Does the system vary? Does the missing starlight match the released heat? A real candidate should become more coherent as these observations accumulate. Its different properties should point toward the same explanation. The visible dimming, infrared temperature, orbital behavior, and independent signals should form one physical system. False candidates often separate under sharper observation. The visible light belongs to one object. The infrared light belongs to another. The dimming comes from dust. The radio emission comes from a distant active galaxy. The mystery divides into ordinary parts. A genuine technosignature would resist that division. Every part would remain connected. Imagine a mature nearby star. It shows no dust features. Its visible brightness is lower than expected for its measured mass and temperature. A large fraction of its energy appears as smooth thermal radiation at a few hundred degrees. High-resolution imaging shows that the infrared glow surrounds the star itself. No background galaxy is present. The spectrum lacks familiar minerals and molecules associated with natural disks. The visible light curve contains repeated, sharply structured transits. Their shapes change according to a predictable orbital pattern. Radio telescopes detect a narrow signal from the same system. Optical observatories record occasional laser pulses. Each new instrument makes the technological explanation stronger. That would be unlike every present candidate. It would not merely remain unexplained, it would become organized. Science would still move carefully. Researchers would test unknown dust models. They would search for unusual stellar companions. They would examine instrument calibration. Several observatories would repeat the measurements. The claim might take years to mature, but the system would continue shining. Unlike one brief radio burst, A stellar-scale structure could wait through the entire investigation. It would remain available for another telescope, and another. The answer would not vanish after 72 seconds. It would orbit. For now, the stars continue to appear largely natural. Some are young and dusty. Some are old and quiet. Some dim because fragments pass before them. Some align by chance with distant galaxies. The infrared sky glows with the history of star formation and cosmic dust. Inside that glow, astronomers search for energy that has been reorganized by intention. No confirmed architecture has emerged, but every candidate sharpens the boundary between dust and design. Perhaps another civilization has already answered through a structure around its star. Perhaps its light is already inside a catalog. Perhaps the visible and infrared measurements have not yet been connected correctly. Or perhaps no civilization within the searched region has built anything so large. The present evidence cannot establish the first possibility. It can only continue testing it. The next part of the journey moves closer. Instead of searching around distant stars, it turns toward our own solar system. Because an answer may not be crossing interstellar space now, it may have crossed long ago. A probe could have arrived before radio telescopes existed. An artifact might orbit quietly among asteroids, moons, or distant objects. If another intelligence ever answered Earth or noticed the solar system before humanity began listening, the message might not be a signal at all. It might be something left behind. An answer may not need to travel toward Earth as a beam. It may arrive as an object. A machine can cross space slowly while carrying instruments, memories, and instructions. Unlike a radio pulse, it does not vanish after passing a receiver. It can enter orbit, wait, observe, and perhaps remain for millions of years. This possibility changes the scale of the search. Radio SETI listens across light years. Artifact SETI examines the neighborhood. It asks whether another civilization may have sent probes into the solar system long before humanity developed astronomy, radio, or even language. Such a probe might not approach Earth directly. It could remain near an asteroid. It might orbit the moon. It could hide among distant icy bodies beyond Neptune. It may have stopped functioning long ago, leaving only a silent structure whose shape and composition differ from anything nature normally creates. Or it could remain active. A small machine may observe the solar system quietly, transmitting information toward a star too distant for humanity to recognize the beam. The idea is sometimes associated with a self-contained interstellar messenger called a Bracewell probe. Instead of sending a signal repeatedly across many light years, a civilization could send an intelligent machine toward another planetary system. Once it arrived, the probe could wait. It might monitor radio activity. It could detect when the local species became technological. Only then would it attempt communication. This approach would reduce the delay between question and answer. A transmitter located 400 light-years away requires 400 years for its signal to reach Earth and another 400 years for a reply to return. A probe already waiting near Earth could respond within seconds. The distant civilization would still receive the probe's report much later, but humanity's first conversation could occur locally. The machine would act as an ambassador, separated from its creators by time. This concept assumes that advanced technology can remain reliable across extraordinary durations. A probe crossing between stars may travel for thousands of years. It must survive radiation, dust impacts, mechanical aging, and long periods without repair. It must navigate accurately. It may need to manufacture replacement parts or awaken only when necessary. These challenges are immense. They do not obviously violate physics. Human spacecraft have already crossed the outer boundary of the Sun's influence and entered interstellar space, though they move far too slowly to reach another star on any practical human timescale. A more advanced civilization might build faster craft. It could use nuclear propulsion, light sails, fusion, antimatter, or methods not yet engineered. Even a slow probe becomes powerful when time is abundant. At 1% of the speed of light, a machine would cross 10 light-years in about 1,000 years. The journey is long to a human life. It is short compared with the age of the Milky Way. A civilization able to launch automated probes for millions of years could explore many nearby systems without breaking the speed of light. The process could accelerate if each probe built copies of itself from local materials. One machine arrives at a star. It studies asteroids and moons. It gathers metals and other resources. Then it constructs several new probes and sends them toward neighboring systems. Each generation repeats the process. These hypothetical machines are called self-replicating probes. The concept is simple in outline and extraordinarily difficult in practice. Replication requires mining, chemistry, manufacturing, computing, energy, and error correction. A machine must distinguish useful materials from harmful ones. It must build components precise enough for interstellar travel. Small mistakes could accumulate through generations, yet biology demonstrates that self-replicating systems can spread across a planet using local matter. Technology might eventually imitate part of that ability. A network of probes expanding through the galaxy could, in principle, reach enormous numbers of stars within a time much shorter than the Milky Way's age. This leads to a variation of the Fermi paradox. If self-replicating probes are possible, and if even one civilization launched them long ago, why has humanity not found one? Perhaps no civilization has built them. Perhaps replication is too difficult. Perhaps probes avoid inhabited worlds. Perhaps they are too small, too quiet, or too carefully disguised to detect. Perhaps they arrived before humans existed and later failed. Or perhaps the solar system has not been examined closely enough. The final possibility deserves careful scale. Earth feels thoroughly explored because satellites map its surface, spacecraft visit planets, and telescopes survey the sky. Yet the solar system is vast. Most asteroids are known only as points of light. Many distant objects remain undiscovered. The surfaces of small moons have been photographed at limited resolution. The deep interiors of planets are inaccessible. Stable orbital regions contain immense volumes. A probe only a few meters across could remain invisible, unless it passed near a telescope or reflected sunlight in a recognizable way. An artifact does not need to be hidden deliberately. Distance can hide it. A dark object near Jupiter's orbit receives far less sunlight than one near Earth. Its reflected light may be incredibly faint. If its surface absorbs most visible radiation, ordinary optical surveys may miss it. If it releases little heat and does not transmit strongly, infrared and radio instruments may also fail to notice it. The object could remain present without producing an obvious signal. This is why artifact searches often focus on locations where a long-lived machine might naturally remain. Stable orbits are attractive. A probe entering the solar system must spend energy to change speed and direction. Once captured, it may choose a region requiring little additional fuel. The Moon offers several possibilities. Its surface preserves ancient material for long periods because it lacks wind, flowing water, and widespread geological recycling. An object placed there millions of years ago might remain partly intact, though impacts, radiation, and extreme temperature changes would gradually damage it. The Moon's far side would also be shielded from much of Earth's radio noise. A probe designed to observe the planet quietly might find it useful. But the lunar surface is enormous. Even high-resolution orbital images do not make every small object easy to distinguish from rocks, shadows, and spacecraft debris. A strange shape in one image would not establish an artifact. Sun angle changes shadows dramatically. Natural boulders can form geometric-looking patterns. Camera processing can produce apparent edges. A convincing lunar artifact would require more than appearance. Its spectrum might reveal unusual metals or manufactured compounds. Its dimensions could show repeated symmetry. Radar might reveal internal structure. A lander could examine it directly. Until such evidence exists, unusual shapes remain geology. The stable gravitational regions associated with Earth and the Moon also attract attention. In a rotating system, there are positions where gravitational and orbital effects combine in predictable ways. These are called Lagrange points. Some provide relatively stable locations for spacecraft. Human observatories already use them. A probe waiting near one of these regions could observe Earth while making only modest orbital corrections. But these areas are not perfectly empty or permanently stable for every orbit. Objects move through complex paths. Solar radiation pressure alters small craft. The gravitational influence of the Moon and planets changes trajectories slowly. A machine may need active control to remain for extremely long periods. Asteroids provide another possibility. They are numerous, ancient, and rich in useful materials. A probe could land on one, enter orbit around it, or disguise itself among nearby debris. From a practical perspective, an asteroid can supply metals, carbon, water-bearing minerals, and shielding. A machine built to repair or replicate itself may treat an asteroid as both home and resource. Yet hiding among asteroids is not as simple as matching one shape. Astronomers measure an asteroid's brightness, spectrum, rotation, and orbit. A metallic object may still resemble a naturally metal-rich asteroid. A smooth artificial surface might become roughened by impacts over time. Dust could accumulate. The probe may become visually ordinary. Its artificiality might only appear through composition, internal cavities, active motion, or an unexplained energy source. The outer solar system offers still greater concealment. Beyond Neptune lies a vast population of icy bodies. Many are small and extremely faint. Their orbits can take centuries or thousands of years. A probe could remain among them, far from human spacecraft and outside the region observed most intensively. But such distance would make monitoring Earth more difficult. The sun would appear faint. Communication would require greater power or narrow beams. If the probe's purpose were only to preserve a record or mark the system, distance may not matter. If it were designed to watch technological development, a closer orbit would be more efficient. There is no reason to assume one ideal location. Different purposes lead to different choices. A beacon may remain near the edge of the solar system, visible to arriving spacecraft. A scientific observer may orbit Earth's moon. A relay may wait near the sun. A resource-gathering machine may use asteroids. A dormant archive might rest beneath a planetary surface. Artifact SETI therefore resembles archaeology without a known site. Researchers must decide where an unknown builder would place an unknown object for an unknown purpose. The search cannot examine everything equally. It begins with locations that combine visibility, stability, and scientific accessibility. One especially intriguing category is interstellar objects. These are natural bodies that enter the solar system from the space between stars. Their paths are not gravitationally bound to the sun. They arrive at high speed, curve around the sun, and leave again. The first recognized example was discovered in 20. It was named Oumuamua, a Hawaiian word often translated as a messenger or scout arriving from the distant past. The name was poetic. It did not establish an artificial origin. Oumuamua's orbit showed clearly that it came from outside the solar system. Its brightness changed strongly as it rotated, suggesting an unusually elongated or flattened shape. No resolved photograph revealed its surface. All shape estimates came from the way its reflected light varied. The object passed close to the sun and then moved outward. As astronomers tracked it, they found a small acceleration that could not be explained by gravity alone. Comets often show this behavior. Solar heat warms their ice. Gas escapes and acts like a weak thruster. But Oumuamua displayed no obvious bright cloud of dust and gas like those surrounding many familiar comets. This combination created uncertainty. An interstellar object with an unusual shape, no obvious coma, and unexplained acceleration naturally attracted speculation. One proposed interpretation suggested that it might be extremely thin and affected by sunlight pressure, perhaps resembling a light sail. A light sail is a large reflective surface pushed by photons. Sunlight carries momentum. When photons strike the sail, they transfer a tiny force. Across enough area and time, the force can alter a spacecraft's speed. Human engineers have already demonstrated solar sailing on small scales. An artificial sail entering the solar system could therefore experience a subtle acceleration without releasing gas. The possibility received enormous public attention, but possibility is not evidence of design. Natural explanations remained. Oumuamua may have released gases that were difficult to detect. Its surface may have changed during long exposure to cosmic radiation. It could contain volatile substances, unlike the water-rich comets most familiar near Earth. The dust surrounding it may have been too faint or composed of particles difficult to observe. Later models explored the release of hydrogen trapped within irradiated ice, the sublimation of nitrogen or carbon monoxide-rich material, and other mechanisms. No one explanation has been accepted universally. The object left the inner solar system before detailed follow-up became possible. This makes Oumuamua similar to the WOW signal in one important respect. The event occurred before humanity understood how valuable it would become. The object was discovered only after it had passed closest to the sun and was already moving away. Astronomers had limited time. Its brightness faded quickly. No spacecraft could intercept it. No close image could reveal whether it was a rocky shard, an icy fragment, a flattened body, or something else. The available observations were enough to establish that it was interstellar and unusual. They were not enough to establish technology. A strange natural object and an artificial object can appear similar when viewed as one unresolved point of light. A sail may be thin and reflective. A natural fragment may also be flat. A probe may accelerate through radiation pressure. A comet may accelerate through gas. An artifact may rotate. A rock may tumble. Artificiality must be shown through a feature that natural models cannot reproduce convincingly. Perhaps a future interstellar object will change direction deliberately. It may reduce speed, enter orbit, or approach one planet with precision. Its acceleration could vary in steps, indicating controlled thrust. It might transmit. Radar could reveal a hollow symmetrical structure. A spacecraft could photograph repeating components. Any of these would be stronger than unusual shape alone. Oumuamua did none of them clearly. It followed a path through the solar system and continued outward. Its non-gravitational motion was small. No confirmed radio transmission was detected. No image resolved an engineered structure. The scientific description therefore remains an unusual interstellar object of uncertain natural composition, not an alien probe. The debate surrounding it still had value. It forced astronomers to consider how quickly another interstellar visitor might need to be studied. Surveys now search the sky more frequently. Future observatories are expected to discover more objects entering from beyond the solar system. A larger sample will reveal whether Oumuamua was truly exceptional or simply the first example of a broad natural population. The first member of any category often looks strange because there is nothing similar for comparison. Before pulsars, one precise radio clock seemed artificial. Before fast radio bursts, 1 millisecond flash lacked a family. Before interstellar objects, Oumuamua's properties had no nearby precedent. The second recognized interstellar visitor appeared in 20. It was named 2I Borisov. Unlike Oumuamua, it behaved much more clearly like a comet. It developed a visible coma and tail. Gas and dust escaped as sunlight warmed it. Its chemistry could be studied. Borisov showed that at least some objects entering from other stars resemble the comets already known within the solar system. This strengthened the expectation that planetary systems naturally eject enormous numbers of icy and rocky bodies. Gravitational encounters with planets can throw comets outward. Young systems can scatter debris. Over billions of years, the galaxy may become filled with wandering fragments. Interstellar visitors therefore do not require interstellar engineers. Natural planetary formation produces them abundantly. But their existence also proves something important for artifact SETI. Objects can cross from one star system to another. The journey is physically ordinary. A small body can drift through interstellar space and enter the solar system without propulsion. A civilization could attach a machine to such an object or shape one deliberately. It could use natural debris as transport, shielding, or disguise. An incoming comet may carry an artificial device beneath its surface. Again, this is a possibility rather than evidence. It shows only that the pathway exists. Interstellar objects may also transport chemistry. They can carry ice, carbon-rich material, and complex molecules between systems. Some hypotheses suggest that natural bodies could even move microorganisms or prebiotic compounds, though survival across ejection, radiation, long travel, and atmospheric entry creates severe challenges. This idea is known broadly as panspermia. It concerns the movement of life, or its ingredients, not intentional communication. If life reached Earth through natural transfer, the event would not be an answer from an intelligence. It would represent biological connection across worlds. But a deliberate probe carrying organisms, genetic information, or artificial seeds would blur the distinction. A civilization might spread life rather than messages. Its answer could be biological. This possibility leads to a far more difficult search. A radio signal announces difference. A biological seed may become part of the planet. If life on Earth were connected to life elsewhere, the evidence might exist inside cells rather than spacecraft. Similar genetic structures on two worlds could indicate shared ancestry, but no extraterrestrial organism has been found for comparison. Earth's biology therefore remains one isolated sample. Some speculative ideas imagine deliberate patterns hidden within genetic code. A civilization might encode a message in organisms designed to survive. But ordinary evolution changes genomes. Mutations accumulate. Sequences disappear. Natural selection reshapes information. A message intended to last billions of years would need extraordinary redundancy and careful placement. No accepted scientific evidence shows that terrestrial DNA contains an extraterrestrial artificial message. Complexity alone is not enough. Biology naturally produces enormous complexity through evolution. A genuine encoded message would require unmistakable mathematical organization, knowledge unavailable to the organisms carrying it, or another feature that natural processes cannot reasonably generate. Without that, the genome is evidence of life's history on Earth, not proof of a sender. Physical artifacts are easier to define, though still difficult to find. A manufactured object may contain alloys uncommon in nature. Its isotopic composition could reveal controlled processing. It may contain layered materials, circuits, cavities, or components arranged for function. The object could show repeated dimensions and precision beyond geology. These features would survive even if the machine had stopped operating. A probe may become a fossil of engineering. Meteorites provide one possible route for discovery. Thousands fall upon Earth. Most are fragments of asteroids, the Moon, Mars, or other natural bodies. They are classified through minerals, chemistry, isotopes, and texture. An artificial fragment entering the atmosphere could be mistaken initially for an unusual meteorite. It might melt, break apart, or become contaminated, but detailed analysis could reveal refined metals, composites, or internal structures. No accepted meteorite has been shown to be extraterrestrial technology. Claims require careful separation from human debris. Rocket stages, satellites, aircraft parts, industrial slag, and metal fragments regularly return to the surface. A manufactured object is not automatically manufactured beyond Earth. Its exposure history, orbit, composition, and context must establish that it arrived from interstellar space rather than from human activity. The modern Earth is surrounded by debris. Thousands of artificial objects orbit the planet. Many are inactive satellites, fragments, or discarded rocket components. Some re-enter the atmosphere. Future archaeologists unfamiliar with the space age might consider them mysterious. Present researchers face the reverse problem. They know human technology is common near Earth. Any suspected alien artifact must first be shown not to be ours. This becomes more difficult as space activity expands. The Moon already contains landers, rovers, impact remains, flags, tools, and discarded equipment. Mars holds spacecraft and landing systems. Asteroids have been touched by probes. Future missions will leave more material. Humanity is beginning to create its own archaeological layer across the solar system. An object discovered centuries from now may require historical records to determine who built it. Artifact SETI therefore benefits from cataloging human hardware accurately. Known spacecraft orbits, mission debris, and landing sites become part of the filter. A genuine unknown should not match any recorded mission. It should also display age, composition, or technology inconsistent with recent human manufacture. Age might be measured through radiation damage, micrometeorite impacts, or surrounding deposits. An object buried beneath ancient lunar soil would be especially interesting if the layer above it formed long before spaceflight. The geological context could show that the artifact arrived millions of years ago, but reaching such an object would require extraordinary luck or a targeted search. The Moon's surface is constantly disturbed by impacts. Material becomes mixed. Small objects can be buried, exposed, or destroyed. A probe may survive in one location and vanish in another. Subsurface radar could identify unusual cavities or structures, but natural lava tubes and rock layers create many features. Direct exploration remains necessary. Mars offers related possibilities. Its surface has wind, dust, radiation, impacts, and geological change. An artifact could become buried beneath dunes or sediment. Subsurface ice might preserve material. Lava tubes could shelter machinery from radiation and temperature swings. But Mars is an enormous planet. Human spacecraft have examined only a tiny fraction at close range. A probe could sit beyond the horizon of every rover. No evidence suggests that one does. The absence of detection across a few landing sites says little about the entire surface. At the same time, there is no scientific reason to interpret ordinary rocks or formations as artificial simply because they resemble faces, doors, animals, or machines. Human perception is highly sensitive to familiar shapes. This tendency is called pareidolia. It helps people recognize patterns quickly. It also creates false meaning in random geology. A shadowed hill can resemble a face. A cracked rock may look like a carved panel. A natural opening can resemble a doorway. Higher resolution images usually reveal ordinary terrain. Artifact searches must therefore rely upon measurements, not resemblance. A true structure should remain artificial under different lighting and viewing angles. Its geometry should persist. Its composition should differ. Its surroundings may show excavation, debris, or repeated organization. A photograph that only looks suggestive is not enough. Venus presents another kind of challenge. Its surface is hidden beneath thick clouds. Radar maps reveal broad geological features, but small objects remain difficult to distinguish. The surface temperature and pressure are extreme. A long-lived probe would need extraordinary durability or remain high in the atmosphere, where conditions are gentler. The giant planets offer no solid surface, but their moons provide many stable environments. Some moons contain ice-covered oceans, others are volcanically active. A probe could orbit them, land upon them, or remain within gravitationally stable regions. Yet there is no reason to assume that an alien visitor would choose the locations humans find most interesting. Its goals might be completely different. It may study the sun rather than planets. The inner solar system contains abundant energy. A probe placed close to the sun could power itself continuously, but the heat and radiation would be severe. The sun's brightness would make a small object difficult to see from Earth. Solar observing spacecraft regularly detect comets and asteroids passing nearby. A dark artificial object could resemble them. Again, motion becomes the strongest clue. A machine that adjusts its trajectory deliberately may distinguish itself from natural bodies. Controlled motion is one of the clearest possible technosignatures within the solar system. Gravity predicts how an object should travel. Radiation pressure and outgassing can modify that path. If neither explains repeated course changes, propulsion becomes plausible. A craft might slow before reaching a planet. It may enter orbit rather than pass through. It could maintain position against gravitational drift. Its acceleration might turn on and off. The direction of thrust could align with navigation goals rather than sunlight. These behaviors would be measurable. A signal is not required. The orbit itself becomes the message. Human probes reveal technology this way. Voyager, New Horizons, and planetary spacecraft do not follow purely natural paths. They perform controlled maneuvers. They use gravitational assists. Their trajectories pass selected targets with extraordinary precision. An external astronomer tracking them accurately could infer that they are artificial even without receiving communication. A future interstellar visitor behaving similarly would deserve immediate attention. Rapid response would be essential. An object moving through the solar system may remain observable for months or years, but interception requires preparation. A spacecraft cannot usually be designed, built, and launched after the object is already leaving. Missions may need to wait in space. A rapid response probe could remain ready near Earth or in a solar orbit. When an interstellar visitor is discovered, the spacecraft changes course. It approaches, photographs, analyzes gas and dust, measures magnetic fields, and perhaps collects material. Such a mission would transform interpretation. A point of light becomes a world. A suspected sail becomes a surface. A strange acceleration becomes measurable gas or controlled thrust. The difference between natural and artificial could become obvious at close range. Even if every visitor proves natural, the science would remain extraordinary. Each object carries material formed around another star. It offers direct access to distant planetary systems without traveling to them. An interstellar comet is a sample delivered by the galaxy. Artifact SETI benefits from the same mission whether the result is technology or geology. This overlap makes the search scientifically productive even when no artifact appears. The hunt for unusual objects improves asteroid surveys. It maps stable orbital regions. It develops rapid spacecraft. It strengthens planetary defense. It studies lunar and Martian geology. It creates better catalogs of human debris. The question of alien technology becomes one reason to understand the solar system more completely. A search can fail to find artifacts and still reveal new natural populations. This is similar to radio astronomy discovering pulsars while listening for intelligence. Technosignature research often produces ordinary astronomy along the way. The most difficult issue remains expectation. What would an alien probe look like? Science fiction often imagines smooth metallic craft with lights, windows, and recognizable symmetry. Real engineering is shaped by function. An interstellar probe may be small, dark, and heavily shielded. Its exterior may resemble rock because thick natural material protects electronics from radiation and dust. It may have no visible openings. Its communication beam may be narrow. Its waste heat may be minimal. After millions of years, impacts and dust could make it even more natural looking. A machine designed by a non-human intelligence may not match human ideas of machines at all. Its structure could be biological. It might grow, repair itself, or use materials that blur the boundary between organism and device. It could be distributed across many tiny units. Instead of one probe, a cloud of microscopic machines might explore a system. Each unit would be almost impossible to find. Together, they could gather information and communicate through weak, coordinated signals. The answer could be present at scales our surveys do not examine. At the opposite extreme, an artifact may be enormous. A transmitter could occupy an asteroid. A habitat might orbit in darkness beyond Neptune. A star shade could alter sunlight. A probe could rearrange small bodies into a geometric pattern. Large size increases visibility, but also energy and material requirements. There is no reason to know which scale is most likely. This uncertainty encourages searches based upon effects rather than appearance. Unusual motion, unusual heat, unusual radio emission, unusual reflection, unusual composition, unusual geometry that persists across observations. A probe may look unfamiliar. Its physical consequences still follow universal laws. It must move through gravity. It must exchange energy. It must interact with light. It must contain matter. These interactions provide common ground. Perhaps the most haunting artifact possibility is also the simplest. A message may be sitting in plain sight, but inactive. No heat, no signal, no motion beyond orbit. Only an object. A dead probe could remain indistinguishable from rock until touched. The solar system contains countless rocks. Searching all of them is impossible with present technology. This creates a limit, different from the radio search. A transmitter can announce itself across great distance. A silent artifact may require physical proximity. The object could already be known as an asteroid with an ordinary catalog number. Its orbit has been measured. Its brightness has been recorded. Nothing demands closer attention. Only a future mission reveals a manufactured interior. This possibility cannot be excluded. It also cannot be used as evidence. An undetected artifact and no artifact produce the same observations. Science moves forward by identifying measurements that separate them. Better spectra can test composition. Radar can test shape and internal structure. Thermal observations can reveal heat. Long-term tracking can reveal acceleration. Spacecraft can approach. The unknown becomes testable one layer at a time. No confirmed extraterrestrial probe, artifact, or machine has been found within the solar system. No lunar image has revealed verified non-human technology. No asteroid has been shown to be manufactured. No interstellar visitor has displayed behavior requiring intelligent control. The search remains open because the territory is enormous, and the observations are incomplete. But openness is not confirmation. A possibility becomes evidence only when a specific object presents measurable artificial features. Until then, the solar system is known to contain natural planets, moons, comets, asteroids, dust, ice, plasma, and the growing remains of human exploration. Yet the thought remains quietly powerful. Radio signals can pass before listeners exist. Laser pulses can miss Earth. Civilizations can rise and vanish while light crosses the galaxy. An artifact is different. It can wait. A machine placed near the moon 1 million years ago may still be present when a species finally learns to search for it. The builders may be gone. Their star may have changed. Their language may be unknowable. But the object could remain. It would be an answer without a conversation. Proof that someone once looked toward this system and decided to cross the dark. Perhaps no such object exists. Perhaps the solar system has never been visited. Perhaps the distance between stars has preserved every world in isolation. Or perhaps the answer arrived before humanity asked the question. The final part of this journey turns toward that uncertainty. It gathers the signals, flashes, atmospheres, structures, and possible artifacts together. It asks what would truly count as an answer, and whether humanity may already possess a fragment of one without yet understanding what it means. The universe has sent humanity many signals. Some arrive as slow waves from hydrogen drifting between stars. Some pulse with the turning of neutron stars. Some flash for less than a heartbeat as magnetars release stored energy. Some appear as narrow lines inside radio data, briefly resembling the beginning of a deliberate transmission. Others arrive through the light of distant planets, carrying traces of atmospheres, clouds, heat, and chemistry. Every signal contains information, but information is not always a message. A star reveals its temperature without intending to communicate. A planet reveals its atmosphere without knowing that it is being observed. A cloud of hydrogen releases radio energy because the laws of physics allow it. A machine would be different. Its signal would contain a pattern created for a purpose. The central challenge is not detecting something unusual. Astronomy detects unusual things constantly. The challenge is demonstrating intention. This is why the question, "Have aliens already answered us?" cannot be resolved by mystery alone. The wow signal remains mysterious, but its mystery does not identify its sender. BLC-1 appeared to arrive from the direction of Proxima Centauri, but deeper analysis connected it to human-made interference. Pulsars once seemed almost mechanical. They became rotating neutron stars. Fast radio bursts seemed unlike anything known. At least some now connect clearly to magnetars. Tabby's star dimmed in extraordinary ways. Its changing colors pointed toward dust rather than enormous artificial structures. Infrared candidates that appeared to surround nearby stars have sometimes separated into ordinary stars and distant background galaxies when sharper telescopes examined them. Oumuamua crossed the solar system with unusual properties, but no observation showed controlled motion, communication, or manufactured structure. Each case began near the edge of the known. Most moved closer to nature as more information arrived. This does not mean that researchers were wrong to investigate them. The investigation is the reason their nature became clearer. A search that never follows unusual signals would never discover anything new. A search that declares every unusual signal artificial would lose the ability to distinguish discovery from imagination. Science moves between these extremes. It remains open. It also remains patient. The first confirmed answer may begin with something that resembles an earlier false alarm. A narrow radio line may appear. At first, it may look like interference. A brief laser pulse may arrive. At first, it may resemble a satellite reflection. A planet may show an unusual atmospheric gas. At first, the feature may seem like an instrumental error. A star may emit too much infrared radiation. At first, dust may appear to be the most reasonable explanation. The candidate becomes important only when additional observations refuse to make it ordinary. A real technosignature should grow stronger under examination. Its direction becomes more precise. Its pattern repeats. Independent observatories recover it. Its behavior follows the motion of a distant world. Its structure contains relationships that natural systems do not produce easily. Its different properties support one another. Radio, light, chemistry, heat, and motion begin telling the same story. The evidence becomes connected. Imagine a narrow transmission appearing from a nearby star. One telescope detects it. Then another telescope, separated by thousands of kilometers, detects the same signal. The frequency drifts slowly. The direction remains fixed against the background stars. The drift repeats every few days. Astronomers compare the timing with the orbit of a known planet. The two patterns match. The transmitter seems to move with the planet. Inside the signal, pulses appear in groups. 2, 3, 5, 7, 11. Then the sequence changes. A second layer begins. The intervals describe geometric relationships. The transmission repeats the information several times, perhaps allowing errors introduced by interstellar space to be corrected. Radio interference databases reveal no terrestrial source. Satellites cannot explain the motion. The star shows no flare. No known plasma process produces the narrowness or mathematical structure. Observatories across the world continue detecting it. At that moment, the signal would no longer be interesting simply because it was unexplained. It would be interesting because explanation after explanation pointed toward technology. Even then, the word alien would require care. The signal could come from an automated machine. Its builders might no longer exist. It could originate from a probe traveling through that system, rather than from a native civilization. The transmitter might be human technology, sent into space in the distant future and observed through some unexpected path. Though distance and chronology would need to support such an extraordinary possibility. Every alternative would be tested, but the artificial nature of the signal could become established before the identity of its creator. Humanity may first discover technology without discovering anyone directly. A machine can speak for absent builders. A beacon may repeat a message placed into it thousands of years earlier. A structure can reveal design after its civilization has changed. A polluted atmosphere can preserve the history of an industrial period. The answer may therefore be archaeological rather than conversational. It may say only that another technological process existed. That single fact would still transform humanity's understanding of life. It would show that nature produced technology, at least twice. Earth would no longer be the only known world where matter became organized enough to study the universe and alter its surroundings deliberately. The discovery would not explain how common intelligence is. Two examples cannot describe an entire galaxy. But the difference between one example and two is profound. With only Earth, the probability of technological life remains almost unconstrained. Life may arise easily wherever conditions permit, or it may be an event so rare that Earth is alone across enormous distances. A second origin would prove that the path can repeat. Scientists could compare the environments. Did both worlds possess liquid water? Did both orbit stable stars? Did technology arise after billions of years? Did the other civilization use biology, machines, or something blending both? Even a distant signal with little content would begin a new science. The location of the transmitter would matter. A confirmed signal from Proxima Centauri would show that technology developed almost next door. A signal from the opposite side of the Milky Way would prove that intelligence exists, but say less about how densely it is distributed. A message from another galaxy would reveal technology operating on scales and across distances beyond present expectations. The closer the source, the greater the possibility of continued study. A nearby planet could be examined for atmospheres, moons, climate, and other technosignatures. Future spacecraft might eventually travel there, but even the nearest star remains far beyond current crewed travel. At the speeds of today's fastest spacecraft, the journey would require many thousands of years. Communication would arrive first. A conversation with Proxima Centauri would still unfold slowly. A message requires more than 4 years to cross the distance. A reply requires more than 4 years to return. One exchange would span almost a decade. Questions would need to be chosen carefully. The sender of each message might not remain alive when the reply arrived. Institutions would carry the conversation across generations. The communication would resemble shared books more than spoken dialogue. At greater distances, the delay becomes even deeper. A civilization 1,000 light-years away sees Earth as it was 1,000 years ago. It does not see modern cities, satellites, or radio telescopes. If humanity detects its signal today and replies, the response reaches the source 1,000 years from now. Any reply to that response returns after another 1,000 years. A complete exchange spans 2 millennia. The original civilization may change before hearing from Earth. Humanity may change before receiving its next message. Interstellar communication joins societies across time as much as space. This means that an answer may already have been sent without yet reaching us. Earth's earliest strong radio emissions have traveled only a small distance compared with the Milky Way's diameter. Most of the galaxy has no way to know that a technological civilization currently exists here. A society 100 light-years away may only now be receiving the radio traces of the early 20th century. A society 500 light-years away still sees Earth before telescopes were invented. A civilization several thousand light-years away observes a planet whose most obvious large-scale activity is biological. It may detect oxygen. It may suspect life. It cannot yet detect humanity's recent technological transformation through light that has not arrived. The galaxy may be quiet, because news travels slowly. Every world lives inside an expanding sphere of information. Earth's sphere contains ancient sunlight, atmospheric signatures, and a thin outer layer of recent radio technology. Another civilization's sphere may already be crossing the solar system. Its oldest biological evidence could have arrived millions of years ago. Its first technological signals may be approaching now, or they may have passed long before anyone was listening. Signals do not wait. A radio pulse crossing Earth during the age of dinosaurs continued onward. A laser flashing across the solar system before telescopes existed left no record. A message aimed at this region could miss the planet because Earth was on the opposite side of the Sun when the beam arrived. Timing can separate civilizations even when distance does not. The Milky Way is more than a collection of places. It is a collection of histories that rarely align perfectly. One civilization may rise while another sleeps. One begins listening after another stops transmitting. A beacon operates for 10,000 years, then fails 1 century before a receiver is built. Two technological societies can exist within the same galaxy without overlapping in a detectable way. This possibility is sometimes hidden beneath the phrase cosmic silence. Silence may not mean emptiness. It may mean misalignment, the wrong direction, the wrong frequency, the wrong century, the wrong instrument. The signal may be narrow while the search is broad. It may be broad while the search is narrow. It may use neutrinos, gravitational waves, or another method humanity has not learned to use efficiently. It may rely upon physical probes rather than electromagnetic communication. It could be encoded within apparently random noise. The sender may assume that any capable receiver understands a scientific principle humanity has not yet discovered. A message can be present and remain unreadable. Human history contains many examples of writing that survived after its language was forgotten. The marks were visible, their meaning was absent. Only after scholars found patterns, related texts, or a key such as the Rosetta Stone did the writing become readable again. An alien signal may create a much larger version of the same challenge. There may be no shared biology, no shared culture, no shared senses, no common objects beyond mathematics and physics. Even mathematics may be represented in unfamiliar ways. Humans use symbols shaped by hands, eyes, writing surfaces, and cultural history. Another intelligence may communicate through dimensions, timings, or relationships that are not immediately obvious. The message might need to teach the receiver how to read it. A well-designed interstellar transmission could begin simply. Repeated units establish counting, patterns introduce arithmetic, spatial relationships introduce geometry, atomic frequencies provide measurements. The message gradually builds a shared language from universal observations. This is why prime numbers and hydrogen are often discussed in SETI. They are not expected because every civilization must find them beautiful. They are expected because they arise from structures in nature that different observers can measure independently. A civilization cannot assume that humans understand its words. It can assume that humans live in the same physical universe. But another sender may have no interest in being understood. The signal could be leakage from ordinary technology. Human radio and radar were not created mainly for distant astronomers. They emerged from communication, navigation, defense, research, and daily life. An alien observer detecting Earth may first see a pattern never intended as a greeting. It might recognize artificial radio energy without decoding a television broadcast. Humanity could encounter another civilization in the same indirect way. A narrow signal reveals a machine. A cluster of artificial atmospheric compounds reveals industry. A night-side glow reveals organized energy use. No formal answer is sent, yet the planet answers simply by existing. This may be the most realistic first discovery. Not a message beginning with a greeting. Not an image of another being. Not a spacecraft descending toward Earth. A spectrum, a light curve, a repeating frequency, a chemical imbalance. Evidence strong enough that nature no longer appears sufficient. The emotional meaning would be enormous. The scientific evidence might remain visually modest. A graph with one unusual line could carry the first confirmed sign of another technology. The public may expect certainty to arrive in one dramatic moment. In practice, confirmation could unfold over months or years. One team reports a candidate. Other researchers request the data. Different models are tested. Observatories schedule follow-up time. The signal returns. Independent instruments recover it. Natural explanations are proposed and removed. The confidence increases gradually. There may be no single second when the entire world agrees. Instead, a threshold is crossed. At first, most researchers say the signal is interesting. Later, they say it is difficult to explain naturally. Eventually, the artificial interpretation becomes the simplest one remaining. The discovery becomes real through accumulation. This slow approach protects humanity from mistakes. False announcements would carry lasting consequences. A natural signal, labeled alien too quickly, could weaken trust in future discoveries. Scientific caution is not an attempt to make the universe less extraordinary. It is an attempt to ensure that the extraordinary conclusion survives. The protocols discussed within SETI emphasize verification, transparency, independent confirmation, and communication with the scientific community. A discovery would not belong to one observatory alone. The source would be visible from much of Earth. Other instruments could test it. Data would need to be shared. Governments, researchers, and international institutions would likely become involved, especially if the signal contained information or appeared directed specifically toward Earth. The question of replying would be separate from the question of detection. Receiving a signal does not require humanity to answer immediately. The light travel time may make urgency unnecessary. A message from a star 100 light-years away has already traveled for 100 years. Waiting months or years to study it changes little from the sender's perspective. This time could allow broad discussion. Who speaks for Earth? Should a response represent science, culture, biology, history, or everyday life? Should it contain mathematics only? Should it acknowledge uncertainty? Should it be transmitted once or repeatedly? Humanity has no global agreement that resolves every possibility. But the first discovery itself may encourage cooperation. Every nation, language, and generation belongs to the same planet. A signal from another world would make that shared location impossible to ignore. Earth would become one small source among the stars. Its differences would remain real. Its common origin would become more visible. The sender's intentions would probably remain unknown at first. A beacon may be welcoming. It may be automatic. It may have no emotional meaning at all. It could simply announce coordinates, scientific knowledge, or the existence of the transmitter. Humanity should not project familiar motives onto an unfamiliar intelligence. Another civilization may not organize itself around individuals. It may be biological, synthetic, distributed, or blended. Its sense of time may differ greatly. A machine operating for 1,000,000 years may treat a century as a short interval. A species living for only a few days may communicate through institutions lasting longer than any individual. The word they may not describe the sender accurately. There may be one system, many systems, an archive, a planet-wide intelligence, a collection of independent machines. The answer may come from something that does not resemble a civilization in the human sense. Yet technology would still reveal choice. Matter has been arranged toward function. Energy has been directed. Information has been preserved. These qualities create the bridge. Humans may not understand the builders, but they can recognize that physical processes were shaped intentionally. The first confirmed technosignature would also change the interpretation of silence elsewhere. If one civilization is found, astronomers can estimate how difficult it was to detect. They can ask how many similar signals may remain below current sensitivity. The discovery method would guide new surveys. If the first evidence is industrial chemistry, more telescopes would examine atmospheres. If it is a laser, optical monitoring would expand. If it is a probe, artifact searches would transform. One answer creates a map toward others. Perhaps the first detection will reveal that technological life is common but quiet. Many planets may contain civilizations whose signals are weak, narrow, or temporary. Perhaps the first signal will come from a rare nearby exception within an otherwise silent region, or perhaps humanity will continue searching for centuries without confirmation. Long silence would itself become information. As surveys improve, astronomers can exclude stronger forms of technology across greater distances. They may show that powerful continuous beacons are rare, that obvious stellar engineering is uncommon, that nearby planets lack industrial atmospheres detectable at certain levels. The universe would still contain possibilities, but the boundaries would become clearer. A search without discovery is not meaningless. It measures the space where answers are not. Yet present silence remains far from complete. Humanity has not monitored every star continuously. It has not examined every useful radio frequency. It has not searched every pulse duration. Most exoplanet atmospheres remain unknown. Rocky worlds are extraordinarily difficult to study. The solar system has not been inspected meter by meter. Infrared surveys cannot distinguish every blended source. Many technological forms may lie beyond present imagination. The search has begun. It has not finished. This is why the most honest answer to the title question contains both caution and wonder. Have aliens already answered us? No confirmed extraterrestrial answer is known. No radio signal has survived every test. No laser has repeated with verified artificial structure. No distant atmosphere contains a confirmed industrial signature. No star is known to be surrounded by extraterrestrial engineering. No artifact has been identified within the solar system. The famous candidates remain natural, terrestrial, unresolved, or incomplete. But the absence of confirmation does not prove that nothing has arrived. A genuine signal may have passed unnoticed. An artificial pattern may remain inside old data. A distant civilization's response may still be traveling. A planetary technosignature may already be present within light that current instruments cannot separate clearly. An artifact could exist where no spacecraft has looked closely. These possibilities remain open because the search is incomplete. They are not discoveries. They are reasons to continue. Perhaps the first answer will arrive tomorrow as a narrow radio line. Perhaps it arrived decades ago and waits inside an archive. Perhaps it has been shining around another star for thousands of years. Perhaps Earth has not yet entered the correct beam. Or perhaps the galaxy truly contains long stretches of living silence. Any of these outcomes would teach humanity something profound. A confirmed signal would reveal company. Continued silence would reveal rarity. Both possibilities make Earth more precious. If life and intelligence are common, this world belongs to a much larger cosmic story. If they are rare, Earth carries something the universe may produce only under exceptional conditions. Either way, the oceans, forests, minds, memories, and questions present here are not ordinary simply because they are familiar. They are matter becoming aware of the stars. For now, humanity listens. Radio dishes turn beneath the night. Optical instruments watch for flashes too brief for human eyes. Spectrographs divide planetary light into delicate chemical patterns. Infrared telescopes search for heat around distant suns. Survey cameras track objects entering the solar system. Computers return to old observations and ask new questions. The search continues quietly. Most nights bring no candidate. Most candidates become ordinary. But every observation expands the small region of the universe that has been examined carefully. The silence becomes better measured. The instruments become more sensitive. The definition of an answer becomes clearer. And somewhere beyond the edge of present knowledge, another signal may already be moving. It crosses darkness without sound. It passes stars that will never notice it. It carries the history of its source within patterns of light. Perhaps it is aimed toward Earth. Perhaps it is moving in another direction. Perhaps there is no signal at all. The universe does not reveal which possibility is true before the evidence arrives. So the question remains open, not empty, not answered by hope alone. Open in the scientific sense, waiting for a measurement, waiting for repetition, waiting for two distant observatories to see the same impossible pattern, waiting for nature's explanations to fall gently away until intention remains. Until that moment, the candidates are invitations to look more carefully. The WOW signal invites another telescope to return to Sagittarius. Proxima Centauri invites continued study of the nearest planetary system. Fast radio bursts invite deeper understanding of magnetars. Tabby's star invites astronomers to study dust and changing light. Interstellar objects invite rapid missions toward visitors from other stars. Every apparent answer becomes part of the method. The universe teaches humanity how to listen by sending signals that are almost but not quite what it seeks. One day, a signal may cross that boundary. It may remain after every test. It may repeat. It may count. It may reveal a planet turning beneath another sun. And the question asked for generations will change. Humanity will no longer ask whether anyone answered. It will ask what the answer means. For tonight, the sky remains quiet. But quiet is not the same as empty. It is simply the condition in which careful listening begins. The stars remain above you, moving through distances too great to feel. Their light crosses years, centuries, and millennia before reaching Earth. Some of that light began its journey before you were born. Some began before human history. And perhaps, somewhere within the endless flow, there is a pattern made by another mind, not yet confirmed, not yet understood, still traveling, still waiting to be found. As this journey draws to a close, allow the question to become lighter. It does not need to be solved tonight. The telescopes will continue turning, the data will continue gathering, the planets will continue circling their stars. The universe has been unfolding for billions of years, and there is time for its answers to arrive. Let the distant signals fade into the background. Let the stars become small points of quiet light. Let the enormous distances feel gentle rather than empty. Earth is here, warm beneath its atmosphere, turning slowly through the darkness. Around you are oceans, clouds, cities, forests, and countless sleeping lives. Whatever waits beyond this world, you are already part of something remarkable. A living planet capable of looking outward, a small world that sends messages into the night, a world patient enough to listen for a reply. And as one mystery settles, another journey can begin. Nightfall science will continue drifting through the quiet questions of space, life, time, and the universe. For now, let your thoughts become still. Let the stars move farther away. Let the silence become soft. Sleep well, and good night.